Look up at the night sky and you'll see countless points of light, a familiar tapestry that has guided humanity for millennia. But hidden within that apparent serenity are cosmic engines of unimaginable power, stars so colossal they dwarf our entire solar system and burn with a ferocity that defies comprehension. These are the hypergiants, the true titans of our universe, and for decades we've been listening to them. What we've heard has not been a quiet hum, but a symphony of the bizarre, a collection of signals so powerful and so utterly inexplicable that they challenge the very foundations of what we think we know. This isn't just astronomy, it's a frontier, a place where our maps of physics end and the great, dark unknown begins. Today, we are embarking on a journey to the very edge of that unknown, to explore 25 of the most baffling signals ever detected emanating from these stellar behemoths. Imagine a whisper that carries the energy of a billion suns, a rhythmic pulse with no discernible source, or a sudden, deafening burst of static that appears, captivates the world's greatest minds, and then vanishes without a trace. These aren't your average stellar beacons, they are cosmic enigmas, each one a riddle waiting to be solved. Every signal is a story, a fragment of a narrative written in the language of physics that we are only just beginning to learn how to read. This is the raw, untamed voice of the cosmos, speaking to us across impossible distances. So prepare to have your concept of reality stretched. We are about to dive headfirst into a cosmic detective story, one where the clues are encrypted in radiation and the suspects are stars that operate by rules we haven't yet discovered. From patterns that hint at intelligence to energies that shouldn't exist, the phenomena we'll uncover together are more astonishing than any work of fiction. This is a journey into the heart of one of space's greatest mysteries, and by the end you will see the night sky not as a static picture, but as a dynamic, living, and deeply mysterious universe that is actively trying to tell us its secrets. Let's begin. Our journey begins not with a living, burning star, but with the ghost of one, a stellar corpse spinning in the void. The Vela Pulsar is the remains of a massive hypergiant that went supernova thousands of years ago, leaving behind an ultra-dense, city-sized sphere of pure neutron star material, spinning over 11 times every single second. For decades, this pulsar was the very model of cosmic consistency, its lighthouse-like beam of radio waves ticking with a precision that rivaled our best atomic clocks. It was a reliable metronome in the vast silence of space, but then, without any warning, its rhythm began to break. Astronomers watched in disbelief as this celestial timekeeper began to falter. The Vela Pulsar started experiencing what are known as glitches, but these were not minor stutters. They were dramatic, violent events. In a matter of seconds, the pulsar's rotation would suddenly, inexplicably speed up. Imagine a spinning ice skater pulling their arms in to spin faster. That's the kind of rapid acceleration we're talking about, but for an object with more mass than our entire sun. These events defied all the standard models physicists had built to explain pulsar behavior. The changes were too large, too abrupt. This wasn't just a clock losing time, it was a clock that occasionally, and for no discernible reason, started racing forward. The theories to explain this erratic heartbeat are as fascinating as the phenomenon itself. One leading idea points to starquakes. Picture the crust of the neutron star, a material 10 billion times stronger than steel, fracturing under immense strain. This starquake could cause the entire object to suddenly contract, making it spin faster in much the same way that our ice skater spins faster by pulling in their arms. Yet, the scale and frequency of these events in Vela challenge even this dramatic explanation. Another compelling possibility involves the pulsar's interior. Scientists speculate that a superfluid, a bizarre frictionless state of matter, sloshes deep within the star. If this superfluid, which normally rotates independently, suddenly couples with the star's solid crust, it could transfer a massive amount of energy, giving the entire pulsar a powerful rotational kick. But what if the cause isn't internal? Some researchers have pondered the existence of an unseen companion, perhaps a disk of leftover supernova debris or even a small, stealthy planet that occasionally tumbles too close to the pulsar. Its gravitational tug could disrupt the pulsar's spin, creating the observed speed-ups and slow-downs. This introduces a tantalizing element of cosmic interaction, a gravitational dance with a phantom partner we cannot yet see. Each glitch from the Vela Pulsar is a stark reminder that even the corpses of dead stars are dynamic, violent, and deeply mysterious places, forcing us to question if we truly understand the fundamental physics governing the most extreme objects in our universe. But just as we were grappling with the erratic behavior of a dead star, one of the most famous living hypergiants in our sky decided to put on a show of its own that sent a ripple of excitement and concern across the entire globe. Shifting our gaze from the southern constellation of Vela to the familiar shoulder of the hunter Orion, we come to our second signal, the great dimming of Betelgeuse. This red hypergiant, a star so colossal that if placed at the center of our solar system, it would engulf the planets out to the orbit of Jupiter, suddenly and dramatically began to fade in late 2019. For centuries, it had been one of the brightest, most recognizable beacons in the winter sky, a prominent orange-red point of light. Then, over a matter of weeks, its light output plummeted by an astonishing 60%. To the naked eye, the change was unmistakable. The star that had blazed for millennia was visibly, palpably dimming. This event triggered a firestorm of speculation, both within the scientific community and among the public. The most thrilling and admittedly terrifying hypothesis was that we were witnessing the prelude to a supernova. Betelgeuse is a star nearing the end of its life, a prime candidate to end its existence in a cataclysmic explosion that would, for a few glorious weeks, outshine the full moon and be visible in broad daylight. The dimming, some theorized, could be a sign of the final, frantic convulsions within the star's core as it prepared to collapse. The world held its breath, wondering if we were about to witness a stellar death on a scale not seen in our galaxy since Kepler's supernova in 1604. Telescopes around the world, from amateur backyard rigs to the most powerful orbital observatories, were instantly trained on the star, collecting an unprecedented amount of data. As the data poured in, a more nuanced yet equally fascinating picture began to emerge. The supernova hypothesis, while dramatic, started to lose favor. Instead, the evidence pointed to a massive cosmic sneeze. The leading explanation suggests that Betelgeuse ejected an enormous cloud of superheated gas. As this material traveled away from the star, it cooled, condensing into vast quantities of dark, light-blocking dust. We were not seeing the star die, but rather witnessing it literally shroud itself in its own expelled matter. It was a colossal stellar weather event, a tempest of its own, making that temporarily obscured our view. Another compelling theory points to the star's own dynamic and tumultuous surface. Hypergiants like Betelgeuse are not smooth, uniform spheres of light. They are roiling cauldrons of massive convection cells, like bubbles in a pot of boiling water, but on a scale where each cell can be as large as our entire sun. Astronomers propose that a simultaneous cooling of several of these gigantic cells on the star's surface could have caused a significant temporary drop in the overall brightness we perceive from Earth. This would be an intrinsic change in the star's behavior, a rhythmic pulse on a grand and unpredictable scale. A more exotic idea involves a circumstellar disk, a vast, uneven ring of cold, dark debris left over from the star's formation or from past eruptions. If our line of sight to Betelgeuse happened to pass through a particularly dense clump within this disk, it would naturally dim the starlight, much like a thin cloud dims the sun. The Great Dimming was ultimately a temporary phenomenon. By mid-2020, Betelgeuse had returned to its normal brilliance, but its legacy is profound. This event provided astronomers with a front-row seat to the volatile late life stages of a supergiant star, offering a real-time case study of processes that were previously only theoretical. It taught us that these titans can undergo violent, episodic mass loss in the form of giant dust clouds, which is a crucial piece of the puzzle in understanding how they enrich the interstellar medium with the heavy elements necessary for planets and life. The event was a powerful reminder that the cosmos is not a static exhibit, but a living laboratory where monumental changes can happen within a human lifetime, challenging our assumptions and rewarding our vigilance with a deeper glimpse into the life cycle of the universe's most magnificent beast. If the Vela Pulsar represents the erratic ghost of a dead star and Betelgeuse a living titan momentarily veiling itself, then our next signal introduces a system that is nothing short of a cosmic battlefield. Nestled within the Carina Nebula, a sprawling stellar nursery of gas and dust, lies Eta Carinae, a binary hypergiant system so volatile and energetic that it defies simple categorization. This isn't a serene pairing of stars, it's a frantic, violent dance between two behemoths on the brink of catastrophe. The primary star is a luminous blue variable, a rare and unstable type of hypergiant that could explode at any moment, and it's orbited by a smaller, yet still immensely powerful hot companion star. Their 5.5-year orbital dance is the engine for one of the most spectacular and perplexing light shows in the galaxy. To understand the modern mystery, we must first look back to its violent past. In the 1840s, Eta Carinae underwent what astronomers call the Great Eruption. For over a decade, it became the second brightest star in the entire night sky, an event completely unprecedented in the modern astronomical record. This wasn't a supernova, the star somehow survived. Instead, it ejected an enormous amount of mass, over 10 times the mass of our Sun, creating the beautiful, expanding bipolar lobes of gas we now call the Homunculus Nebula. This eruption left behind a system shrouded in its own debris, a permanent scar from a stellar temper tantrum of unimaginable scale. It set the stage for the ongoing turbulence we observe today. In recent decades, as our observational tools have grown more sophisticated, a new and specific mystery has emerged from within this chaotic environment: periodic, highly energetic X-ray bursts. As the two stars swing through their elongated orbits, their immense stellar winds rivers of charged particles blowing off their surfaces at millions of kilometers per hour violently collide. This collision creates a permanent, seething shock front, a region of superheated plasma that constantly glows in high-energy X-rays. This background roar is expected. The puzzle is the series of sharp, dramatic flares that erupt within this already tumultuous environment. These aren't random spikes, they follow a peculiar periodicity, flaring up at specific, predictable points in the orbital cycle. Yet their intensity and precise timing are not fully explained by the simple mechanics of the two stars' orbits. So, what could be causing these scheduled yet explosive outbursts? The most straightforward theory involves the clashing stellar winds, but with a twist. As the stars move along their elliptical paths, the distance between them changes dramatically. When they are at their closest approach, or periastron, the winds slam together with ferocious intensity. One leading idea suggests that dense clumps or knots of material within the primary star's wind could be plowing into the shock front, creating localized explosions that register as these sharp X-ray flares. It would be like throwing logs onto a bonfire, creating sudden, brilliant bursts of light and heat against the already roaring flames. A more complex theory points to the star's magnetic fields. Magnetic reconnection is a process seen on our own Sun, where magnetic field lines cross, snap, and reconfigure, releasing vast amounts of energy in solar flares. At Eta Carinae's scale, this process could be magnified to an almost incomprehensible degree. If the magnetic fields of the two stars briefly interact and reconnect during their close passes, the energy released could easily power the observed X-ray outbursts, creating a temporary, star-spanning electrical circuit of cosmic proportions. Perhaps the most intriguing possibility is that a third, unseen actor is influencing this binary drama. Some astrophysicists have proposed the existence of a massive planet or even a small, dim star orbiting the primary hypergiant. The gravitational influence of this hypothesized third body could be periodically perturbing the primary star's wind or distorting the shock front between the two stars. This could create a regular schedule of instability, a gravitational nudge that trips the system into flaring at precise intervals that the simple two-body orbital mechanics cannot fully account for. Each of these X-ray flares is a direct telegram from the heart of this stellar chaos, forcing us to question whether we are watching a simple duet or a far more complex and crowded cosmic ensemble. While the chaotic duet of Eta Carinae showcases the raw physical power of hypergiants, our next signal presents a mystery of a completely different caliber, one that for decades has been the holy grail for those searching for signs of intelligent life beyond Earth. We now turn to a signal so iconic that its name alone evokes a sense of awe and tantalizing possibility, the WOW signal. Detected on a warm August evening in 1977 by the Big Ear radio telescope at Ohio State University, this burst of radio noise was so powerful and so perfectly conformed to what scientists expected from an artificial transmission that the volunteer who found it, Jerry Amon, simply circled the alphanumeric code on the printout and scribbled, "Wow." In the margin, for 45 years, it has stood as perhaps the best candidate for a message from another civilization. But what if we've been looking for the wrong kind of sender? A compelling, though controversial, new theory suggests the source of this legendary signal may not have been a distant intelligence, but a distant hypergiant. To understand why this idea is so revolutionary, we first need to appreciate the signal's extraordinary characteristics. It was a strong, narrowband signal, meaning it was concentrated on one specific radio frequency, the hydrogen line at 1420 MHz. This is significant because hydrogen is the most common element in the universe, and scientists have long proposed that this would be a logical, watering hole frequency for interstellar communication. The signal also exhibited a pattern of rising and then falling intensity over exactly 72 seconds, which is precisely the duration the Big Ear telescope would expect as a source moved through its fixed field of view due to Earth rotation. This perfect signature ruled out a terrestrial origin like a passing airplane or satellite. It came from somewhere in the direction of the constellation Sagittarius, and then after that single, brilliant 72-second burst, it was never heard again despite numerous and frantic follow-up searches. It was a one-time shout into the cosmic void. The traditional assumption was that such a purposeful, artificial-seeming signal must be the product of a technology. However, the hypergiant theory proposes a different kind of cosmic engine. The region of space from which the WOW signal is thought to have originated is not an empty void. It contains a star known as 263-1a. This star is a yellow hypergiant, a massive and incredibly luminous star in a volatile stage of its life. The new hypothesis asks a simple but profound question. Could a natural process associated with such a stellar titan produce a signal that mimics an artificial broadcast? The answer may lie in a phenomenon known as a maser, which stands for microwave amplification by stimulated emission of radiation. Think of a maser as a natural cosmic laser, but for radio waves. In the vast, swirling molecular clouds that often surround hypergiant stars, certain molecules, like water or hydroxyl, can become pumped with energy by the star's intense radiation. Under the right conditions, this energy is then released in a powerful, coherent, and narrowband burst of radio emission. It's a natural amplifier, and a hypergiant-powered maser could, in theory, produce a signal with the precise intensity and frequency profile of the WOW signal. Instead of a carefully crafted message, we might have been listening to the blast of a stellar-powered natural siren. This theory, however, is fraught with its own set of challenges. The primary issue is one of location. Despite decades of analysis, astronomers have never been able to pinpoint the WOW signal's origin with absolute certainty. The Big Ear telescope used 2 feed horns, and the signal was only detected in one of them, which means its exact celestial coordinates remain frustratingly ambiguous, confined to 2 potential patches of sky. While a star like 263-1 lies within one of these candidate areas, confirming it as the definitive source is like trying to identify a single person who shouted in a packed, echoing stadium. Furthermore, the sheer power required for the signal is immense. Could a natural maser, even one powered by a hypergiant, be energetic enough to produce a signal that, after traveling hundreds of light years, would still be so strong that it dwarfed all background noise? Some scientists are skeptical, arguing that the power requirements push the limits of known astrophysical processes. Yet, this very controversy is what revitalizes the mystery. The hypergiant origin theory doesn't solve the case of the WOW signal. It effectively reopens it. It forces us to move beyond a simple binary choice of either human interference or aliens, and to explore a much richer, more complex middle ground populated by the most extreme natural objects in the cosmos. It challenges us to consider that the universe might be capable of creating signals that are, for all intents and purposes, indistinguishable from artificial ones using nothing but the known laws of physics operating at their most extreme limits. This new perspective transforms the WOW signal from a potential hello into a different kind of message, one that reminds us that nature, in its most magnificent and powerful forms, still holds profound secrets and can still produce phenomena that stop us in our tracks and make us say, wow. From the tantalizing mystery of the WOW signal, we now venture to a star that doesn't just whisper enigmatic radio bursts, but rather screams its instability across the cosmos with the force of a stellar temper tantrum. Let's turn our attention to Rho Cassiopeiae, a yellow hypergiant so immense and unstable that it makes the drama of Betelgeuse seem almost placid by comparison. Nestled within the familiar W shape of the Cassiopeia constellation, this star is a true ticking time bomb, and its outbursts are among the most violent and poorly understood events we have ever witnessed in our galactic neighborhood. What sets Rho Cassiopeiae apart are its cataclysmic surface eruptions, events of such staggering scale that they redefine the very meaning of a stellar flare. We are not talking about mere solar prominences here. On at least 3 documented occasions in the last century, in the 1940s, 2000, and 2013, Rho Cassiopeiae underwent convulsions where it violently ejected a mass of material equivalent to our entire Sun. To put that in perspective, our Sun will lose only a tiny fraction of its mass over its entire 10 billion-year lifespan. Rho Cassiopeiae can shed that much in a single, explosive event that lasts just a few months. This is mass loss on a truly biblical scale. For astronomers watching from Earth, these events unfold as a dramatic and rapidly changing cosmic light show. The star's visible brightness can plummet by a factor of nearly 2, as its own ejected material forms a vast, temporary shroud of cooling gas and dust that blocks its light. But the real story is told through spectroscopy, which analyzes the star's light to reveal its chemical composition. During an eruption, the star's spectrum, its unique light fingerprint, undergoes a radical transformation. The familiar signatures of elements get scrambled, and for a brief period, the spectrum makes it look as if the star has temporarily transformed into a much cooler, different type of star altogether. This is the direct evidence of the star literally tearing off its own outer layers and hurling them into the void, revealing deeper, hotter layers beneath in a process that is both destructive and revealing. So what could possibly trigger such apocalyptic self-destruction? The leading theories point to processes occurring deep within the star's unstable heart. One prominent idea involves thermal pulses. In the final, frantic stages of a massive star's life, the core can experience spasmodic bursts of nuclear fusion in shells surrounding its central engine. These pulses generate tremendous waves of energy that travel outward, eventually reaching the surface with enough force to blow a significant portion of the star's atmosphere into space. It's a deep-seated nuclear instability that manifests as a surface catastrophe. Another compelling theory focuses on the immense power of light itself. In hypergiants, the outward pressure of radiation, the sheer force of all the light photons pushing outward, is almost strong enough to counteract the star's own crushing gravity. In this delicate balance, even a slight increase in brightness can make the star's outer layers become gravitationally unbound. It's a phenomenon known as reaching the Eddington limit. In this state, the star becomes so luminous that its light literally starts pushing its own atmosphere away, not in a steady wind, but in a sudden, catastrophic ejection, like a geyser finally boiling over. Yet a third possibility lies in the star's own turbulent interior. Hypergiants are dominated by gigantic convection cells, vast plumes of hot plasma that rise from the interior, cool at the surface, and then sink back down. In a star as large as Rho Cassiopeiae, these cells are on a scale we can barely comprehend. Some astrophysicists suggest that particularly massive convective plumes, or the collision of several such cells, could generate powerful shock waves that travel upward and blast material clear off the star's surface. This would be a purely hydrodynamic explosion, a burp from the star's deepest digestive system. Each of these theories has its merits, but none can yet fully account for the precise timing and staggering mass loss we observe. Rho Cassiopeiae remains a supreme example of a star operating at the very edge of physical stability, offering us a violent and spectacular preview of the fate that awaits many of the Milky Way's most massive inhabitants. If you thought the violent eruptions of Rho Cassiopeiae were extreme, wait until you encounter a star that is actively building its own cosmic tomb. Our sixth signal leads us to the remarkable hypergiant known as IRC plus 10,420, a star that presents us with a profound paradox. It is one of the brightest objects in our entire sky when viewed in infrared light, yet it remains almost completely invisible to the naked eye. This startling discrepancy is the heart of the mystery. The star is radiating a truly enormous and unexplained excess of infrared energy, a telltale sign that it is not shining freely into space, but is instead cloaked within a vast, complex, and incredibly dynamic shroud of its own making, a colossal envelope of cosmic dust. So, what exactly is generating this incredible infrared glow? The process is both elegant and destructive. The intense visible and ultraviolet light pouring from the hypergiant's scorching surface slams into the surrounding cloud of dust grains, tiny particles of silicates and other heavy elements. These microscopic specks absorb that high-energy starlight, heat up to temperatures of hundreds of degrees, and then re-radiate that absorbed energy back out, but now at much longer, lower energy wavelengths, infrared light. It's a cosmic bait and switch. We see a brilliant infrared beacon because the star's true visible light has been absorbed and converted by this immense dust shell. This isn't a thin, wispy haze. Data from powerful infrared observatories like the Spitzer Space Telescope and the Herschel Space Observatory reveal a nebula of truly staggering proportions, a structure so immense it could engulf our entire solar system many times over. The intrigue deepens when we look at the structure of this dusty shroud. Detailed observations show that this envelope is not a simple, smooth sphere gently expanding outward. Instead, it is a chaotic, lumpy, and highly asymmetric structure filled with intricate knots, arcs, and shells of material. This complex geometry is a frozen record of violence. It tells us that the star has not been losing mass in a steady, gentle wind like our own sun does. Instead, the dust shell bears the unmistakable scars of recent, violent, and episodic formation events. It's as if we are looking at the geological strata of a mountain, where each layer of dust corresponds to a specific cataclysmic eruption in the star's recent past. Three-dimensional models constructed from this data reveal a tumultuous history, showing concentric shells of material that have been ejected at different times and are now expanding outward at different speeds, colliding and merging in a slow-motion celestial ballet. This brings us to the central enigma: what physical mechanism is powerful enough to drive such prolific and chaotic dust production? Astronomers are actively investigating several compelling possibilities, each with dramatic implications for the star's fate. The first theory posits that we are witnessing a star in a state of hyperactive, continuous mass loss. In this scenario, the star's own incredible luminosity, its sheer brightness, is acting like a constant gale force wind, relentlessly pushing its outer atmosphere into space. As this ejected gas travels away from the star, it expands and cools, allowing atoms to condense directly into solid dust grains, much like water vapor condensing into snowflakes in cold air. This process could be steadily building the dusty cocoon we observe. A second, and perhaps more likely, theory suggests that IRC plus 10,420 is experiencing a series of violent episodic eruptions, similar to but perhaps even more frequent than those of Rho Cassiopeiae. The star may be undergoing powerful convulsions, possibly driven by the same kind of deep-seated thermal pulses or radiation pressure instabilities. Each of these eruptions would blast a colossal amount of fresh gas into the surrounding environment, providing a sudden, massive infusion of raw material for dust formation. The lumpy, shell-like structure of the nebula strongly supports this idea of discrete, explosive events rather than a smooth, continuous flow. Perhaps the most intriguing hypothesis involves an unseen partner. Could a binary companion star be stirring the pot? If IRC plus 10,420 is not alone, the gravitational tug of war with another star could be profoundly disrupting its outer layers. This interaction could strip material away more efficiently, funnel it into a disk, or trigger instabilities that lead to enhanced and asymmetric dust production. The irregular shape of the dust envelope is a key piece of evidence that points toward some kind of external influence, a gravitational dance that is actively sculpting the star's final act. Each of these theories paints a picture of a star in a state of extreme transition, frantically shedding its own skin as it races toward its ultimate demise as a supernova. The mysterious infrared excess of IRC plus 10,420 is more than just a strange signal. It is a direct glimpse into the violent and beautiful process of a stellar giant preparing for its final bow. But just when you think you've seen the full spectrum of hypergiant weirdness, along comes a star that turns its entire surroundings into a natural laser light show, broadcasting on frequencies we can barely comprehend. Our journey now takes us to the spectacular red hypergiant NML Cygni, a star so deeply shrouded in its own expelled matter that it's practically invisible in optical light. Its voice is not one of visible eruptions or infrared excess, but of intense, highly structured microwave emissions that behave in ways that defy our understanding. This star is home to some of the most powerful masers ever discovered, and their strange, unpredictable behavior is rewriting the book on stellar astrophysics. To understand the mystery, you first need to grasp what a cosmic maser actually is. Imagine a laser, but instead of producing a tight beam of visible light, it generates an intense, coherent beam of microwave radiation. The name itself gives it away: microwave amplification by stimulated emission of radiation. In the vast, cold molecular clouds that envelop a hypergiant like NML Cygni, molecules like water vapor and silicon oxide are constantly bathed in the star's intense radiation. This incoming energy pumps the molecules, boosting their electrons to higher energy states. It's a cosmic version of winding up a spring, When another microwave photon of just the right frequency happens to pass by, it can trigger these excited molecules to release their stored energy all at once in phase, creating an amplified, coherent burst of radiation. Think of it like a perfectly timed cheer rippling through a stadium crowd, where one voice triggers a powerful, unified roar. This process transforms the star's circumstellar envelope from a quiet cloud into a brilliant, natural microwave amplifier. Now, what makes NML Cygni's masers so bizarre isn't their existence, but their behavior. Standard maser models predict a certain level of stability and predictable variation. But the masers from this star are wildly erratic. They show extreme flux variations, meaning their brightness at microwave frequencies can skyrocket or plummet by enormous factors over surprisingly short timescales, sometimes in a matter of weeks. Even more puzzling is their polarization. The microwaves coming from NML Cygni are highly polarized, meaning their electromagnetic waves are oscillating in a preferred, aligned direction. This is a clear signature of the influence of powerful, organized magnetic fields, but the strength and structure of these fields implied by the observations are far more complex than anything our current models predicted for a star of this type. It's as if we're listening to a powerful, clear radio station that suddenly changes its broadcast strength and then starts twisting its signal in a way that suggests a magnetic force field of unimaginable complexity is at work. So, what cosmic engine could be driving this chaotic microwave symphony? Astronomers are investigating several compelling hypotheses, each pointing to the extreme physics at play around this stellar titan. One leading idea focuses on the star's own violent pulsations. Red hypergiants are inherently unstable, rhythmically expanding and contracting like a giant cosmic heart beating. These pulsations generate powerful shock waves that propagate outward through the circumstellar envelope. When one of these shock fronts slams into a region of water or silicon oxide molecules, it could violently compress and heat the gas, providing a sudden, enormous burst of energy that super pumps the masers, causing their dramatic brightening. The subsequent fading would then correspond to the relaxation of the gas after the shock wave has passed. This would make the maser activity a direct audio-visual representation of the star's own internal heartbeat. A second theory delves deeper into the strange geometry of the environment. The envelope around NML Cygni is not a smooth, uniform shell. It's incredibly clumpy and asymmetric. Observations suggest vast, dense clouds of molecules are moving independently within the overall outflow. In this scenario, the bizarre maser variations we see might not be due to changes in the pumping energy, but simply due to our changing line of sight through this lumpy, dynamic fog. As these dense clumps of maser-emitting material drift across our view, they can act as natural amplifying lenses, focusing and intensifying the signal. When they move out of the way, the signal drops. This would mean we're not seeing the engine itself change power, but rather watching the swirling, turbulent smoke from the engine occasionally coalesce into brighter plumes. Perhaps the most fascinating hypothesis involves the star's magnetic field. Hypergiants are not generally thought to possess highly ordered, large-scale magnetic fields like those of pulsars. However, the intense polarization of NML Cygni's masers is a screaming clue that such a field may indeed be present and incredibly powerful. This magnetic field could be threading the entire circumstellar envelope, organizing the molecules and aligning them like tiny compass needles. This alignment is what produces the polarized signal. The variations could then be explained by changes in this magnetic field itself, perhaps due to dynamo action deep within the star's convective interior, or from the twisting and shearing of field lines by the chaotic motion of the clumpy outflow. We could be witnessing the real-time activity of a stellar magnetic field of unprecedented scale and power, a force actively shaping the very medium through which the star's voice is projected. The bizarre masers of NML Cygni are more than just a curiosity. They are a sophisticated diagnostic tool, allowing us to sense the invisible forces of magnetism and shock waves that govern the final, turbulent years of a star that truly operates in a league of its own. Now we shift our focus from the microwave mazes of NML Cygni to a different, far more violent part of the electromagnetic spectrum. Prepare to encounter a star that doesn't just broadcast its instability, it screams it in the language of pure, raw energy. Our eighth signal brings us to the Wolf-Rayet hypergiant known as WR25, a star so extreme it makes our previous giant seem almost tame. This is a stellar object in its final, frantic act, having blasted away its own outer hydrogen layers to reveal a searingly hot, helium-burning core that is exposed to the vacuum of space. WR25 is essentially a stellar nucleus operating without a protective atmosphere, and from this cosmic forge, astronomers have detected something that should not be possible. Brief, incredibly powerful flares of gamma-ray radiation, the highest energy light in the universe. The discovery of these gamma-ray flares was as dramatic as the events themselves. They were picked up by space-based observatories like the Fermi Gamma-Ray Space Telescope, instruments designed to detect the most energetic phenomena in the cosmos, from colliding black holes to supernova explosions. The data revealed sudden, sharp spikes in gamma-ray flux originating directly from the vicinity of WR25. These were not the steady, high-energy glow expected from the star's turbulent wind. These were distinct, explosive outbursts. Each flare was incredibly brief, lasting only a few hours, but in that short time, they would release more energy in gamma rays than our Sun emits across all wavelengths in decades. This is a level of power that immediately ruled out ordinary stellar processes and pointed to something far more exotic and poorly understood occurring in the star's immediate environment. To unravel this, we need to look at the unique engine of a Wolf-Rayet star. WR25 possesses a stellar wind of almost incomprehensible ferocity. This isn't the gentle solar breeze our Sun produces. It is a hurricane of charged particles blowing off the star's surface at speeds approaching 3,000 kilometers per second. This wind is so dense and powerful that it carries away a mass equivalent to our entire Earth every single year. This relentless outflow creates a perpetually chaotic and high-energy environment around the star, a perfect breeding ground for particle acceleration. The leading theory for the gamma-ray flares involves this very process. Within the tumultuous shock fronts and turbulent collisions of the wind itself, subatomic particles like electrons could be accelerated to velocities infinitesimally close to the speed of light. When these ultra-relativistic particles then collide with photons of starlight or with other particles in the wind, they can produce gamma rays through processes known as inverse Compton scattering or proton-proton collisions. It's a natural, stellar-scale particle accelerator, but the sporadic, flaring nature suggests this process isn't always smooth. It must occasionally and violently go into overdrive. So, what cosmic switch could be flipping this particle accelerator to its highest setting? One compelling idea points to magnetic reconnection, a phenomenon we see on our Sun but magnified to a hypergiant scale. While Wolf-Rayet stars are not typically known for strong, organized magnetic fields like those of neutron stars, it is possible that WR25 possesses a complex and powerful magnetic field tangled within its furious wind. If this field were to suddenly reconfigure, snapping and reconnecting its magnetic field lines, it would unleash a catastrophic torrent of energy, rather like a cosmic-scale short circuit. This single, colossal event could instantly accelerate a vast swarm of particles to extreme energies, resulting in the brief, brilliant flash of gamma rays we observe as a flare. The entire stellar environment would, for a few hours, become the site of a magnetic explosion of staggering proportions. Another fascinating possibility, and one that is gaining traction, involves an unseen dance partner. WR25 is widely believed to be part of a binary system, orbited by a hot, massive O-type companion star. The gravitational and hydrodynamic interaction between these two titans is a recipe for cosmic violence. As the two stars swing through their orbit, their respective hurricane force winds slam into each other, creating a permanent, seething shock front between them. This colliding wind region is a natural hotspot for particle acceleration and gamma-ray production. The flares could then be explained by instabilities within this region. A sudden buildup of density or a particularly violent compression as the stars reach their closest orbital approach could trigger a runaway acceleration event, turning the entire wind collision zone into a temporary gamma-ray beacon. This would mean the signal isn't coming from a single star, but from the explosive interface where two stellar powerhouses meet. The unidentified gamma-ray flares from WR25 force us to confront the limits of our knowledge about the final stages of stellar evolution. They suggest that the deaths of the most massive stars are not just about a final, singular supernova explosion, but are punctuated by violent, precursor outbursts that tap into fundamental forces in ways we are only beginning to model. Each of these gamma-ray flashes is a stark, high-energy telegram from the edge of stellar physics, challenging us to understand how a star can, in its final millennia, become a natural engine for the universe's most powerful form of light. While the gamma-ray fury of WR25 represents the cutting edge of high-energy astrophysics, our next signal takes us on a journey not just through space, but through time itself, connecting the observations of 17th century astronomers with the most advanced technology of the 21st. We now turn to the remarkable story of P Cygni, a hypergiant whose violent adolescence was witnessed by stargazers over 400 years ago and whose past continues to literally echo back to us today. This star provides a rare and precious bridge between historical astronomy and modern astrophysics, offering a long-term case study of hypergiant instability that is utterly unique in the heavens. The historical record of P Cygni is where this mystery truly begins. In the year 1600, this star was completely unknown, invisible to the naked eye. Then, in the summer of 1600, Dutch astronomer Willem Bleeu recorded the sudden appearance of a new, third-magnitude star in the constellation of Cygnus, the Swan. For 6 years, it blazed brightly before fading from view once more, a classic nova of the era. But P Cygni was not done. It erupted again in 1655 and then again in 1665, each time flaring to visibility before dimming back down. This erratic behavior confounded early astronomers who had no framework for understanding a star that could repeatedly ignite and fade in this way. It was a celestial variable of a type never before documented, a true rebel in the seemingly fixed and orderly cosmos of the time. These historical outbursts were the first clues that P Cygni was no ordinary star, but a volatile behemoth in the throes of a tumultuous early life. Today, we classify P Cygni as a luminous blue variable, one of the rarest and most unstable types of star in the universe. It is in a precarious evolutionary phase, hovering on the edge of the so-called Eddington limit, where the outward pressure of its own intense radiation almost overcomes the inward pull of its gravity. The historical outbursts were, in fact, colossal eruptions where the star violently expelled huge shells of its own atmosphere into space, dramatically increasing its brightness as it shed mass on a scale that is difficult to fathom. These were not true supernova, but rather supernova imposters, events of such stellar violence that they mimic a star's death throes without the final, catastrophic core collapse. The star was, and still is, literally tearing itself apart in its struggle to remain stable. The phenomenon that makes P Cygni's story so compelling for modern scientists is the concept of light echoes. Think of it like this: when the star erupted in the 17th century, light from that explosion radiated outward in all directions at, well, the speed of light. The direct light from the outburst reached Earth centuries ago and was seen by Bleeu and his contemporaries. However, some of that light didn't travel directly to us. Instead, it traveled out into space until it encountered vast, distant clouds of interstellar dust. This light then bounced off those dust clouds like sound echoing off a canyon wall and began a much longer, indirect journey back toward Earth. We are now, in the present day, detecting these reflected photons. We are literally seeing the light from those 400-year-old eruptions, but only now, as the echoes finally complete their long, detoured path to our telescopes. This isn't just a celestial curiosity, it's an incredibly powerful tool. By analyzing these light echoes with instruments like the Hubble Space Telescope, astronomers can perform a kind of forensic archaeology on the ancient outburst. They can take a spectrum of the echo's light, which reveals the chemical composition and temperature of the material ejected during the 17th century events. This allows scientists to compare the star's violent past state with its current, relatively quiescent state. What they've found is fascinating. The spectra from the light echoes show pronounced P Cygni profiles, a specific fingerprint in the starlight characterized by a sharp blue-shifted absorption line next to a broader emission line. This profile is the telltale sign of a massive, expanding shell of gas. The echoes confirm that the historical eruptions involved the ejection of a huge amount of material at incredibly high speeds, providing direct quantitative data about events that were once only qualitative notes in an astronomer's logbook. So, why does a star like P Cygni undergo such dramatic transformations? The root cause lies deep within its internal struggle for equilibrium. As a massive star evolves and burns through its nuclear fuel, its core contracts and heats up, producing ever more energy. This increases the outward radiation pressure. In a luminous blue variable, this pressure becomes so immense that it begins to overpower the star's gravity in its outer layers. The star becomes critically unstable, and its outer envelope effectively becomes unbound, lifting away from the core. This leads to a massive eruption, shedding solar masses of material in an event that temporarily restores a precarious balance. It's a self-regulating, if incredibly violent, process. The star blows off its excess mass to prevent itself from blowing up entirely, a desperate stellar strategy to avoid immediate self-destruction. Modern observations of P Cygni itself, as opposed to its echoes, show that this turbulence is far from over. The star continues to display spectral anomalies and a powerful, gusty stellar wind, indicating that it is still losing mass at a prodigious rate. It is a living laboratory of stellar instability. The combination of historical records, modern observations, and the time-delayed data from light echoes gives us an unparalleled three-dimensional view of a hypergiant's life. P Cygni teaches us that the evolution of the most massive stars is not a smooth, linear process, but a stuttering, episodic one, marked by violent convulsions that reshape the star and its surroundings. This celestial time capsule allows us to watch a single star's story unfold across 4 centuries, confirming that the universe's most powerful giants are in a constant and often explosive state of becoming. If you thought the historical echoes of P Cygni were remarkable, consider a star so immense that its own atmosphere is a roiling, chaotic cosmos in its own right. We now journey to the constellation of Canis Major, home to V Canis Majoris, a red hypergiant that is one of the largest known stars in our galaxy. This is a stellar behemoth of almost mythical proportions, a star so vast that if it were placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. But the true mystery of V Canis Majoris isn't just its sheer scale. It's the strange and ever-changing story told by its very light, a story we can only read by analyzing a property known as polarization. To understand the enigma, let's first demystify what polarization means. Imagine light as a wave traveling through space, wiggling up and down and side to side in all directions perpendicular to its path. This is normal, unpolarized light. Now picture that same light passing through a filter, like the lens of a pair of polarized sunglasses. this filter only allows waves vibrating in one specific direction to pass through. The light that emerges is polarized. Its waves are now all aligned, oscillating in a single, orderly plane. In the vastness of space, this filtering doesn't happen with sunglasses, but through physical processes around a star. When starlight scatters off electrons or dust grains in a star's extended atmosphere, or when it passes through regions dominated by a strong magnetic field, its waves can become aligned or polarized. For astronomers, this isn't just a curiosity, it's a powerful diagnostic tool. By measuring the direction and degree of this polarization, we can infer the physical conditions, shapes, and magnetic forces at work in environments we can never hope to visit directly. What makes Vela Canis Majoris so puzzling are the specific anomalous patterns observed in its polarized light. Standard stellar models suggest that for a spherically symmetric star losing mass in a smooth, steady wind, the polarization should be relatively stable and low. Vela Canis Majoris defies this expectation completely. Its polarization is not only strong, but it is also highly variable, changing significantly over timescales of months and years. Even more baffling is the fact that these pronounced swings in polarization often show little to no correlation with changes in the star's overall brightness. This is a critical clue. It tells scientists that whatever is causing the polarization is not simply tied to the total amount of light the star is producing. Instead, it points to dramatic, large-scale changes in the geometry of the star's immediate surroundings, a profound asymmetry that is evolving right before our eyes. So, what colossal structures could be causing this erratic polarization signature? One compelling theory points to the presence of gigantic starspots. Our own Sun has sunspots, cooler, magnetically active regions on its surface. On a hypergiant like Vela Canis Majoris, these spots would be on an entirely different scale, dark regions potentially larger than the entire orbit of Earth. As the star rotates, these immense spots would move in and out of our view, creating a dramatically asymmetric pattern of light emission. This asymmetry would, in turn, cause the scattered light from the star's extended atmosphere to become polarized in a way that changes with the star's rotation. The unpredictable variability of the polarization could then be explained by the birth and death of these colossal starspots, a dynamic and turbulent surface activity on a scale we can barely conceptualize. Another prominent hypothesis involves the vast, clumpy clouds of dust that we know shroud this star. The envelope around Vela Canis Majoris is known to be incredibly complex, filled with gigantic, discrete knots and arcs of ejected material. If one of these massive, dense dust clouds were to drift into our line of sight, it would act as a natural polarizing filter, scattering the starlight in a specific direction. As different clouds of varying sizes and compositions drift through the atmosphere, they would impose different polarization signals, creating the observed variability. This would mean we are not seeing changes on the star's surface itself, but rather in the chaotic, swirling smoke of its own making, a circumstellar environment of incredible dynamism. Perhaps the most far-reaching theory involves the possibility of a global magnetic field. While red hypergiants are not typically thought to possess strong, organized magnetic fields like those of younger stars, the polarization data from Vela Canis Majoris is a tantalizing hint that one may be present. A large-scale magnetic field could permeate the star's enormous atmosphere, ordering the environment and aligning the dust grains like tiny compass needles. This alignment would naturally produce a polarized signal. The changes in polarization could then be driven by shifts in this magnetic field itself, perhaps due to the star's slow rotation dragging the field lines, or from violent convective motions in its interior twisting and distorting the magnetic architecture. Discovering a coherent magnetic field in such a vast and seemingly chaotic object would revolutionize our understanding of the final evolutionary stages of the most massive stars, revealing an invisible force that actively sculpts their death and the dispersal of their enriched material into the galaxy. The strange, shifting polarization of Vela Canis Majoris is therefore more than a technical curiosity. It is a direct, if cryptic, communique about the violent and asymmetric processes that govern a star in its final, epic struggle against gravity. Leaving behind the dramatic polarization swings of Vela Canis Majoris, we now encounter a hypergiant that presents us with a mystery of a completely different nature, one defined not by violent outbursts but by a profound and unsettling silence. Meet HD 179821, a yellow hypergiant shrouded in a massive envelope of gas and dust. When astronomers point their most sensitive radio telescopes toward this stellar titan, they expect to hear the complex and variable symphony of a chaotic, dying star. Instead, they are met with a steady, unwavering hum. This is the enigma of the silent radio emission, a signal so surprisingly smooth and constant that it challenges our very understanding of how these immense stars lose mass in their final years. The peculiarity of HD 179821 becomes starkly clear when we compare its radio voice to its hypergiant cousins. For stars like NML Cygni or Vela Canis Majoris, radio observations typically reveal a highly variable and noisy signal. The data charts look like a turbulent seismograph, with spikes and dips corresponding to clumps of material ejected at high speed, shock waves rippling through the stellar wind, or the dramatic appearance of new maser spots. This variability is the expected soundtrack of stellar instability. In contrast, the radio spectrum of HD 179821 is remarkably flat. It displays a strikingly steady flux density, a gentle and unvarying curve that persists for years with almost no detectable fluctuation. It's the difference between listening to a crackling bonfire and the faint, consistent drone of a distant power line. This star isn't whispering, it's maintaining a monotone, and in the context of hypergiant behavior, that is profoundly strange. So, what could this unusual tranquility mean for the physical processes at work around this star? The steady radio emission is a direct tracer of the star's mass loss, and its smoothness points toward an exceptionally stable and homogeneous outflow. One compelling explanation is that we are witnessing a hypergiant with a truly well-regulated stellar wind. In this scenario, the star is shedding its outer layers in a continuous, gentle, and remarkably even stream, like a perfectly calm river flowing compared to the turbulent, flash flood rapids of its cousins. This could imply that the star's internal engine, its nuclear fusion core, and the convective zones above it, is operating in a state of rare and temporary equilibrium. The forces of radiation pressure pushing outward and gravity pulling inward may have found a delicate, sustained balance, allowing mass to be expelled in a smooth, continuous current rather than in violent, episodic belches. Another fascinating possibility is that the star's own vast circumstellar envelope is acting as a natural buffer or regulator. The material already ejected might be so extensive and evenly distributed that it actually smooths out any smaller-scale instabilities happening closer to the star's surface. Imagine a chaotic geyser whose explosive bursts are muffled by a deep, placid lake surrounding it. Any clumpiness or shock wave generated near the star could be dissipated and homogenized as it travels through this thick, massive shroud, resulting in the uniform radio glow we detect from Earth. This would mean the star's interior might still be turbulent, but we are simply unable to hear its true voice through the soundproofing of its own creation. The silent signal of HD 179821 forces astronomers to ask a deeper question. Is this star an oddity, or is it showing us a previously overlooked phase of hypergiant evolution? Its steady nature could indicate that it is in a very specific and perhaps very brief transitional state. It might be poised on the brink of a major eruption, having achieved a precarious stability that is destined to shatter. Alternatively, it could represent a more advanced stage where the most violent convulsions have already passed, and the star has now settled into a more orderly, but still massive, final shedding of its remains before its core collapses. This quiet beacon in the radio sky serves as a crucial counterpoint to the drama of other hypergiants, reminding us that the road to stellar death is not always marked by fireworks. Sometimes the most profound mysteries are found in the deepest and most consistent silences. Shifting our focus from the steady radio hum of HD 179821, we encounter a hypergiant that is the polar opposite, a star that doesn't just flare in one wavelength, but seems to ignite its entire being in a coordinated burst of multi-spectral fury. Our 12th signal transports us out of the Milky Way and into its orbiting satellite galaxy, the Large Magellanic Cloud, to the extraordinary star Enceladus. As a luminous blue variable, it is already a member of one of the most unstable stellar classes known. But what sets Enceladus apart is a phenomenon that has left astronomers astounded. Its flares are not isolated events in one type of light. Instead, when this star erupts, it does so simultaneously across the entire electromagnetic spectrum, from the searing fury of ultraviolet light all the way down to the long waves of radio emission. This isn't a series of separate outbursts, it's a single, unified explosion that energizes the star's entire atmosphere at once, a coherence that challenges our compartmentalized understanding of stellar activity. The evidence for this coordinated fury comes from a powerful form of astronomical observation, multi-wavelength monitoring. Imagine a hospital patient hooked up to multiple monitors simultaneously, one tracking heart rate, another brain waves, a third blood pressure. For Enceladus, astronomers use telescopes that are the cosmic equivalents of these machines, each sensitive to a different kind of light. When a major flare occurs, the data reveals something extraordinary. The ultraviolet light from the star's scorching outer layers suddenly spikes. At the exact same moment, the visible light we see with our eyes surges in brightness. And without any perceptible delay, the radio telescopes also record a dramatic increase in signal. When you line up these light curves, these graphs of brightness over time, they all peak in perfect synchrony. This precise alignment is the crucial clue. It tells us that these emissions are not independent phenomena. They are all different symptoms of the same underlying cataclysm. This coordinated brightening presents a profound challenge to explanations that treat stellar flares as localized or piecemeal events. For instance, a common model for radio flares in massive stars involves shocks within the stellar wind, where clumps of fast-moving gas collide. But such an event, occurring far out in the extended atmosphere, would not necessarily cause an immediate and simultaneous flare in the ultraviolet light coming from the star's photosphere, its visible surface. The energy from a localized shock would take time to propagate and influence other parts of the star's vast structure. The fact that all wavelengths brighten in lockstep suggests the driving event is not a surface scratch or a distant wind collision, but a global upheaval. A single, massive disturbance that rocks the star from its core to the outermost fringes of its atmosphere in an instant. So, what kind of cosmic event could trigger this star-wide tantrum? One compelling theory points to a global stellar eruption. In this scenario, a deep-seated instability, perhaps a convulsive pulse in the star's nuclear fusion processes or a wave driven by its immense radiation pressure, rips through the entire stellar structure. This would be akin to a planet-wide earthquake shaking every continent at once. The initial explosion would flood the inner atmosphere with energy, causing the dramatic surge in ultraviolet and visible light. Almost immediately, a colossal blast wave would travel outward, accelerating particles in the stellar wind to relativistic speeds and heating the outer layers to millions of degrees, which in turn generates the simultaneous flare in radio waves. It's a single, titanic energy release that manifests differently across different wavelengths, but all stemming from one common, explosive origin. An equally fascinating and perhaps complementary hypothesis involves a massive, star-spanning magnetic event. While luminous blue variables are not typically known for strong, ordered magnetic fields like those of neutron stars, it is possible that S Doradus possesses a complex and powerful magnetic field tangled within its interior. This idea proposes a process called magnetic reconnection on a truly gargantuan scale. Imagine the star's magnetic field as a vast web of rubber bands stretched to their breaking point. If these field lines suddenly snap and reconfigure, they can release an astonishing amount of stored energy all at once, in an event that would dwarf billions of simultaneous solar flares. This magnetic explosion would inject energy directly and rapidly throughout the star's atmosphere, efficiently powering the ultraviolet emission near the surface while also accelerating electrons in the outer envelope, which then spiral around magnetic field lines to produce the coordinated radio burst. This would mean we are not just witnessing a thermal explosion, but the violent relaxation of a star-sized magnetic spring. The implications of these coordinated flares are far-reaching. They suggest that the most unstable hypergiants may experience eruptions that are fundamentally holistic in nature. The star doesn't just have a troubled spot on its surface, the entire entity can become unstable and release energy globally. This forces astrophysicists to develop new models that treat the star as a single, interconnected system, where a disturbance in the core can have instantaneous repercussions in the stellar wind thousands of stellar radii away. Each synchronized multi-wavelength flare from S Doradus is a stark reminder that when these stellar titans decide to speak, they do so with a unified voice that echoes across the entire spectrum of light, demanding that we listen not just to one part of their story, but to the whole explosive narrative at once. From the coordinated fury of S Doradus, we now turn our attention to a different kind of stellar mystery, one written not in brilliant flares of energy but in the subtle chemical fingerprint of starlight. Gaze toward the constellation Cepheus and you'll find the garnet star Mu Cephei, a red hypergiant whose deep crimson hue has captivated observers for centuries. Yet when astronomers train their most powerful spectrographs on this star, they uncover a puzzle far more complex than its beautiful color. Mu Cephei's light, when broken into its constituent rainbow, reveals a pattern of dark and bright lines that tell a story of bizarre and unexpected chemistry. Its atmosphere appears to be freakishly enriched with specific heavy elements that, according to all our standard models, should be locked away deep in the star's interior, utterly invisible to us. This isn't a mystery of raw power, but of composition, a cosmic recipe that seems to defy the rules of stellar cooking. To understand just how strange this is, we need to understand the S process, which stands for the slow neutron capture process. This is one of the primary ways the universe forges elements heavier than iron. Deep inside an aging, massive star, free neutrons are slowly absorbed by atomic nuclei like iron seeds. One by one, these neutrons are captured, gradually building heavier and heavier elements like strontium, yttrium, barium, and technetium over thousands of years. The critical point is that this alchemy happens in the star's deep, hot core or in a surrounding shell. In a normal, well-behaved star, these newly minted heavy elements should remain trapped deep within, destined to be scattered into space only when the star explodes as a supernova. They should not be present in the star's cool, outer atmosphere that we can observe. Finding them there in such abundance is like finding the molten inner ingredients of a cake already baked into its cool, outer frosting. The spectroscopic data for Mu Cephei makes this anomaly stunningly clear. A spectrum is a star's barcode, with each dark absorption line corresponding to a specific element absorbing light at a unique wavelength. In Mu Cephei's barcode, the lines for these S-process elements are strikingly strong and deep. When astronomers compare its spectrum to that of other, similar red supergiants, the difference is undeniable. Mu Cephei is quite literally dripping with elements that its peers lack. This overabundance isn't subtle. It's a glaring outlier, a chemical signature that demands an explanation for how these deeply forged materials manage to rise to the visible surface against the immense pull of the star's own gravity. So, what extraordinary mechanism could be dredging up these cosmic treasures from the stellar depths? One leading theory involves a process known as deep mixing or convective dredge up. Red hypergiants are titanic cauldrons of convection, with massive plumes of hot plasma constantly rising from the interior and cooler materials sinking back down. It's like a celestial lava lamp on an unimaginable scale. In most stars, this churning only reaches down so far, but in a hypergiant as evolved and unstable as Rho Cassiopeiae, it's possible that these convective currents occasionally plunge much deeper than usual, perhaps even deep enough to tap into the layers where the S process is actively occurring. These superpowered currents could then grab hold of the newly synthesized heavy elements and carry them all the way up to the surface where they become visible in the spectrum. This would be a slow, continuous process of chemical enrichment, a self-pollution from the inside out. A second and far more dramatic hypothesis suggests that Rho Cassiopeiae's strange chemistry is the scar of a violent past merger. Imagine a binary star system where two stars have orbited each other for millions of years. As one star evolves into a giant, it can engulf its smaller companion. The smaller star wouldn't survive. It would be torn apart, its material spiraling into the core of the hypergiant. This cataclysmic event would violently churn the star's interior like a spoon stirring a giant pot. In the process, it could mix deep-seated S-process elements from the core regions up to the surface, while also adding its own unique chemical inventory to the mix. The anomalous abundances we see today could be the permanent chemical residue of a long-ago act of stellar cannibalism, a ghost of a digested companion star forever imprinted on the spectrum of the survivor. Yet a third possibility pushes the boundaries of stellar physics even further. It's conceivable that in the unique and extreme conditions within a hypergiant like Rho Cassiopeiae, with its immense pressures, temperatures, and complex magnetic fields, a previously unknown nucleosynthesis pathway is at work. Perhaps there is a way to produce these S-process elements not just in the deep core, but in intermediate layers much closer to the surface, where they could more easily contaminate the atmosphere we observe. This would mean our current understanding of how stars build heavy elements is incomplete, and that hypergiants operate as specialized nuclear factories with their own unique set of recipes that we are only just beginning to decipher. The strange chemistry of Rho Cassiopeiae thus serves as a critical clue, pointing toward either a profound internal process, a violent historical event, or a completely new chapter in our understanding of how the elements of the cosmos are forged. Just when we thought we had a handle on the varied personalities of hypergiants, the universe delivers a puzzle that seems specifically designed to confound us, proving that some of the most profound mysteries are not just loud and violent, but fleeting and ghostly. Our 14th signal brings us to the remarkable yellow hypergiant HR 5171A, a star so vast it's actually part of a fascinating binary system where the two stars are so close they touch, engulfing each other in a swirling, shared atmosphere. It's a system already known for its dramatic interactions, but it recently offered up a new and very different kind of secret. In its vicinity, astronomers have detected a mysterious, transient X-ray source, a brilliant, high-energy spark that flares into existence and then vanishes back into the darkness, its brief appearance completely decoupled from the known, rhythmic behavior of the hypergiant itself. The discovery came from powerful space-based observatories designed to scan the heavens in the high-energy language of X-rays, like the Chandra X-ray Observatory and XMM Newton. These telescopes don't see the familiar points of visible light. They see the universe in terms of searing heat and violent collisions, mapping the locations of black holes, neutron stars, and supernova remnants. During a routine survey of the region around HR 5171A, an analysis of the data revealed a sharp, distinct spike in X-ray emissions. This wasn't part of the diffuse, hot glow from the Hypergiant's turbulent wind. This was a pinpoint source, a distinct celestial ember that burned brightly for a short period and then, by the time of the next observation, was gone. The most baffling part was its timing. This X-ray flash did not coincide with any particular phase of the complex binary orbit, nor did it match any known periodic change in the star's brightness or spectrum. It was a random, isolated event, a single, unannounced firework in the cosmic night. This fleeting nature is the very heart of the mystery. Transient X-ray sources are not unheard of in astronomy, but they are typically associated with very specific types of objects and predictable behaviors. To find one so close to such a well-studied and unique hypergiant immediately raises a critical and difficult question. Are we seeing a new form of activity from HR 5171 itself? Or is this an entirely separate object that just happens to lie in the same line of sight, a case of cosmic coincidence? The telescope's resolution is incredibly sharp, but in the vastness of space, pinpointing an exact, unambiguous location for such a brief event is notoriously challenging. The source appeared to be very close to the hypergiant, but close in astronomical terms could still mean a separation of trillions of kilometers, leaving room for doubt about a true physical connection. So, what could this phantom X-ray flare be? One of the most compelling theories involves a hidden, compact companion lurking within this already complex system. We know HR 5171 is in a binary dance, but what if there is a third, unseen member, a neutron star or even a stellar mass black hole? In this scenario, the transient X-ray source could be explained by an accretion flare. As this compact object travels along its orbit, it might occasionally pass through a particularly dense clump of material in the hypergiant's prodigious stellar wind. For a brief period, this dense gas would funnel onto the neutron star or black hole's surface or accretion disk, heating up to millions of degrees and releasing a brilliant, short-lived burst of X-rays before the object moved out of the dense stream and the flare subsided. This would make the signal an indirect product of the hypergiant, but not from the star itself, a faint, deadly companion feeding on the Titan's winds. Another possibility is that we are being fooled by a background object, a cosmic interloper completely unrelated to the hypergiant, far behind HR 5171A, deep in the distant reaches of the galaxy. A cataclysm could have occurred. A flaring neutron star, a distant gamma-ray burst, or even the tidal disruption of a star by a supermassive black hole in a far-off galaxy could have produced a powerful, one-time flash of X-rays. From our vantage point, this brilliant but distant event would appear projected right next to the hypergiant, a classic trick of perspective. The challenge for astronomers is that without a repeat performance, it is nearly impossible to rule out this possibility conclusively. The transient source has left no lasting trace to study, making its true distance and nature incredibly difficult to pin down. Perhaps the most intriguing and revolutionary idea is that we are witnessing a completely unprecedented type of hypergiant activity. Could the incredibly complex and dynamic magnetic fields generated in the turbulent interface of the two touching stars in the HR 5171, a system occasionally snap and reconnect on a colossal scale? A single, catastrophic magnetic reconnection event, even larger than those hypothesized for other hypergiants, could theoretically accelerate a vast swarm of electrons to near-light speed in a localized region of the atmosphere, producing a brief but incredibly intense burst of X-ray emission before the system settled back into its usual state. This would be a new, high-energy language in which these stellar titans can speak, a whisper of unimaginable magnetic forces at work deep within their shared embrace. The transient X-ray source near HR 5171 remains an enigma, a ghost in the data that challenges our categories and reminds us that for every answer we find, the cosmos is ready to present a new and even more perplexing question. Leaving behind the ghostly X-ray flicker near HR 5171A, we encounter a star that has perfected the art of the cosmic disappearing act, a stellar Houdini whose vanishing tricks have baffled astronomers for over 2 centuries. Meet our Coronea Borealis, a supergiant star that, while not quite reaching the immense physical size of a hypergiant, possesses its own brand of extreme and enigmatic behavior that makes it a crucial part of our mystery tour. This star's claim to fame is its utterly bizarre and unpredictable light curve, a graph of its brightness over time that looks less like a gentle wave and more like the heartbeat of a patient with a severe, intermittent illness. For years, sometimes even decades, our Coronea Borealis will shine with a steady, reliable brightness, a constant point of light in the northern constellation of Corona Borealis, the Northern Crown. And then, without any warning whatsoever, its light plummets. It can fade by a factor of 100 or even 1,000, becoming a barely detectable ghost of its former self. After a few weeks or months in this deep, dimmed state, it just as mysteriously recovers, brightening back to its normal brilliance as if nothing ever happened. These events are not gradual, they are sudden, dramatic plunges into near invisibility that defy all our conventional models of stellar stability. The secret behind this incredible vanishing act lies not within the star's core, but in its atmosphere's strange chemistry. Our Coronea Borealis belongs to a rare class of stars known as hydrogen-deficient carbon stars. Its atmosphere is an exotic and carbon-rich environment, overflowing with soot-producing elements and largely devoid of the hydrogen that dominates most other stars. This unique composition is the key ingredient for its magic trick. The leading theory, known as the puff theory, proposes that at seemingly random intervals, the star ejects a discrete cloud or puff of carbon-rich gas from its surface. As this blob of material travels outward and away from the star, it expands and cools. Once the temperature drops below a certain critical threshold, the carbon atoms suddenly condense, much like water vapor condensing into snow, forming a cloud of microscopic carbon dust grains right in our line of sight. This dust is exceptionally effective at blocking light. It acts like a vast, dark shade being drawn across the star, absorbing its visible light and re-radiating it as invisible infrared energy. The star hasn't actually grown dimmer, it has simply and very effectively shrouded itself in a cloud of its own soot. The central, enduring mystery of our Coronea Borealis, however, is not the how of the dimming, but the why now. What physical trigger decides the exact moment for a carbon puff to be launched? Standard stellar physics suggests that dust formation should be a more continuous, predictable process, yet the timing and depth of these dimming events are fundamentally chaotic and unpredictable. They show no regular periodicity that would point to a simple rhythmic cause like stellar pulsation. This randomness is the core of the puzzle that models have struggled to solve for decades. Astronomers are investigating several compelling hypotheses to explain this erratic schedule. One prominent idea focuses on the star's own intrinsic pulsations. Our Coronea Borealis is known to vibrate, slowly expanding and contracting. While these pulsations are not perfectly aligned with the dimmings, they could play a crucial role by creating temporary conditions ripe for an ejection. Think of it as the star taking a deep breath. During the expansion phase of a pulsation cycle, the star's outer layers become more loosely bound, its gravity slightly weaker at the surface. This might lower the energy required for a blob of material to overcome gravity and escape, providing the initial nudge that sends a carbon puff on its way. The pulsation sets the stage, but another, more random actor might provide the final push. That final push could come from magnetic activity, Another leading theory posits the existence of gigantic, cooler magnetic spots on the star's surface, analogous to sunspots but on a far grander scale. These spots are regions of intense, localized magnetic fields. If such a spot were to suddenly become unstable and release its pent-up magnetic energy, it could act like a cannon, blasting a concentrated plume of carbon-rich gas off the star's surface. This would make the dimming events less like a gentle exhalation and more like a series of sporadic magnetic sneezes. The unpredictable nature of magnetic reconnection, the snapping and rearranging of field lines, would perfectly account for the randomness we observe in the star's light curve. A third and deeply fascinating possibility involves the star's own radiation pressure as the instigator. In a star so rich in carbon, the outer atmosphere is constantly being pushed outward by the relentless pressure of its own light. Under normal conditions, this outflow might be relatively steady. However, it's possible that this system is teetering on a knife edge of instability. A tiny, almost imperceptible increase in brightness or a slight change in atmospheric opacity could be enough to tip the balance, causing a local region of the atmosphere to suddenly become gravitationally unbound and blow off as a discrete cloud. This would be a case of the star's own light literally pushing it over the edge, a self-triggering instability that occurs only when a very specific and unstable threshold is crossed. The unpredictable dimming of our Coronary Borealis thus stands as a beautiful and frustrating testament to the complex, non-linear physics governing the final acts of rare and exotic stars, a reminder that even with a known mechanism, the cosmos can retain an element of profound and captivating unpredictability. Just when we think we've catalogued every possible form of stellar violence, the cosmos delivers a new, more precise kind of fury. Our journey now takes us to the brilliant, searing beacon of Zeta Puppis, an O-type hypergiant that dominates its corner of the sky with a blistering blue-white intensity. This star is the definition of a cosmic powerhouse, burning at a surface temperature so high over 40,000 degrees Celsius that it makes our sun seem like a dim, cool ember in comparison. But the true mystery of Zeta Puppis isn't just its raw power. It's the specific, gunshot-like manner in which it expels its own substance. For decades, the prevailing model for such massive stars was a steady, supersonic stellar wind, a continuous, albeit powerful, river of charged particles flowing outward into space. Zeta Puppis, however, has been caught firing dense, high-velocity bullets of material, clumps that tear through its own stellar wind at speeds that defy any notion of a smooth, orderly outflow. The evidence for this astonishing phenomenon comes from a forensic analysis of the star's light, using the powerful tool of spectroscopy. When astronomers train their spectrographs on Zeta Puppis, they don't just see a simple, clean fingerprint. Instead, the spectrum of its ultraviolet light reveals a pattern of dark absorption lines that are anything but static. These lines, which are created when specific elements in the star's outflowing wind absorb starlight, should appear relatively smooth and symmetric if the wind were a uniform, streaming plasma. What scientists actually observe is a shocking distortion. These absorption lines are often jagged, exhibiting multiple, discrete, and deeply blue-shifted components. A blue shift means the material is moving toward us at tremendous speed, and the fact that these features appear as separate, sharp sublines is the telltale clue. Each one represents a distinct, dense clump or bullet of material racing toward us along our line of sight, absorbing a specific slice of the star's ultraviolet light. The velocity of these bullets is staggering. They've been clocked moving at thousands of kilometers per second, significantly faster than the star's already ferocious background wind. It's the spectroscopic equivalent of listening to a steady, powerful jet engine and suddenly hearing the distinct supersonic crack of individual bullets firing through the exhaust. This clumpy, bullet-like ejection presents a fundamental challenge to the classic smooth wind model, which has been a cornerstone of stellar astrophysics for decades. That model treats the mass loss from a massive star as a continuous, homogeneous fluid, driven outward by the relentless pressure of the star's own intense radiation. While it can explain the overall rate at which the star sheds mass, it cannot account for these discrete, hypervelocity blobs. The bullets imply a level of violence and structure that is far more localized and explosive. They suggest that the process of mass loss is not a gentle, continuous evaporation, but rather a series of sporadic, cannon-like eruptions from the star's surface. This forces a major revision of our theories, pushing us to identify the specific, powerful mechanisms that can focus stellar material into such concentrated projectiles and launch them with such extraordinary force. So, what cosmic cannon is Zeta Puppis using? One of the leading suspects is the star's magnetic field, operating through a process known as magnetic confinement. While O-type stars like Zeta Puppis are not typically thought to have strong, global magnetic fields like those of neutron stars, it is possible that it possesses a complex, patchy network of local magnetic fields. Imagine a region on the star's surface where magnetic field lines spring up from the interior, creating a powerful, localized arc. This magnetic loop can act as a trap, confining and building up hot plasma beneath it. As pressure mounts, this magnetic bottle becomes unstable and suddenly ruptures, releasing the pent-up plasma in a focused jet, a single high-velocity bullet of stellar material. This would be a stellar-scale version of a solar flare, but with energies magnified millions of times over, capable of punching a dense clump right through the ambient stellar wind. Another compelling idea points to the star's own internal vibrations, specifically non-radial pulsations. Unlike the simple, rhythmic expansion and contraction of a pulsating variable star, non-radial pulsations are far more complex. They are waves that ripple across the star's surface, causing some areas to rise while others fall, like the sloshing of water in a giant, turbulent basin. In a hypergiant like Zeta Puppis, these pulsations could be incredibly powerful. A particularly strong, localized wave crest could rise up and break, much like a massive ocean wave, and in doing so, it could catapult a blob of the star's own atmosphere clear off the surface, giving it that extra kick of velocity. The chaotic and ever-changing pattern of these pulsations would naturally explain why the bullets appear sporadically and from different effective locations on the star's disk. Perhaps the most intriguing possibility involves an unseen partner in this drama. Could Zeta Puppis have a binary companion, a smaller, denser star orbiting dangerously close? The gravitational influence of a companion could create immense tidal forces, violently stirring the hypergiant's outer layers. As the two stars swing through their orbit, these tidal forces could periodically rip large chunks of material from the primary star's surface, flinging them outward at incredible speeds. Alternatively, the companion's gravity could focus and channel the hypergiant's wind, causing it to collide with itself and condense into dense, fast-moving clumps in a process similar to what we see in other colliding wind binaries. The presence of a companion would provide a natural, periodic engine for this violent mass loss, adding a layer of gravitational complexity to the already turbulent life of a stellar titan. The high-velocity bullets of Zeta Puppis are therefore more than just a curious anomaly. They are direct probes of the intense, hidden forces, magnetic, vibrational, or gravitational, that churn within and upon the most massive stars, revealing a level of structural complexity and violence that we are only just beginning to decipher. Now, if you thought the visible and infrared vistas of hypergiants were spectacular, wait until you listen to their voices in a part of the spectrum that reveals the deep cosmic cold. Our 17th signal transports us to an object with one of the most evocative nicknames in all of astronomy, the Fried Egg Nebula, officially known as ERAS 17163-3907. This yellow hypergiant, enshrouded in not one but two immense, nearly perfect concentric shells of dust and gas, truly looks like a cosmic breakfast when viewed in infrared light. But beyond its striking appearance lies a deeper mystery, one that resonates not in visible light or X-rays, but in the faint, long-wave whispers of the submillimeter domain. It's here, in the chilly frontier between infrared and radio waves, that this star broadcasts a powerful and complex signal that reveals the intricate and often baffling physics of its self-constructed prison. To understand what we're hearing, you need to know what submillimeter astronomy can detect. Think of it as the ultimate tool for sensing the cold universe. While optical telescopes see the hot surfaces of stars and infrared telescopes peer through warm dust, submillimeter observatories like ALMA, the Atacama Large Millimeter/Submillimeter Array, are designed to detect the faint glow of objects just a few tens of degrees above absolute zero. This is the realm of frigid interstellar dust grains and, even more crucially, the realm of complex molecules. In the cold, roomy expanses of circumstellar envelopes, atoms have a chance to link up and form intricate molecular structures. Submillimeter telescopes are like cosmic molecular scanners. They can detect the unique rotational signatures of everything from simple carbon monoxide to complex organic molecules, the very building blocks of life as they tumble and spin in the void. When we point these instruments at the Fried Egg Nebula, we aren't just seeing its structure, we are taking a chemical census of its vast, cold outer atmosphere. And what a strange chemical census it is. The submillimeter data for eras 17163-3907 reveals emissions that are far stronger and more complex than standard models predict. The star's circumstellar envelope is a hotbed of molecular activity, with unusual and unexpected emission lines pointing to the presence of specific molecules in abundances that are difficult to explain. The data also reveals a puzzling temperature and density structure within those beautiful concentric shells. The submillimeter maps show that the material isn't smoothly distributed. Instead, it's clumpy and shows signs of being heated unevenly from within. This suggests that the physics of the shell formation isn't as simple as a gentle, expanding bubble. There appears to be ongoing, dynamic activity within these seemingly serene structures, a hidden turbulence that only reveals itself when we listen to the star's cold, submillimeter voice. This brings us to the central enigma of the Fried Egg Nebula. How did those magnificent double shells form in the first place? The exquisite, almost artistic symmetry of the nebula presents a classic cosmic whodunit. Did these shells emerge from a pair of catastrophic periodic eruptions, or are they the product of a continuous but wildly variable stellar wind? The submillimeter observations provide critical clues that support both dramatic possibilities. The case for violent, episodic eruptions is compelling. The two distinct shells we see could be the fossilized remnants of two separate titanic mass ejection events, separated by hundreds or even thousands of years. In this scenario, the star would have been relatively stable for a long period, then experienced a deep-seated instability, perhaps a thermal pulse or a radiation pressure-driven convulsion that blasted its outer layers into space. This material would have expanded outward, forming the first shell. Then, after a long quiescent period, the star underwent a second, similar eruption, ejecting another massive shell that now travels inside the first. The sharp, well-defined edges of the shells seen in submillimeter maps support this idea. They look like snapshots of discrete explosions, cosmic smoke rings frozen in time. The immense scale and mass of these shells strongly suggest they were born in sudden, violent paroxysms, not in a gentle breeze. On the other hand, the case for a continuous but highly variable wind also has its merits. Imagine the star's mass loss not as a series of explosions, but as a wind whose intensity is constantly changing, like a gale that alternates between a strong gust and a hurricane-force blast. In this model, the shells are not formed by single eruptions, but are rather the result of a stop-start process in the stellar wind. A period of extremely high mass loss would eject a dense layer of material. This would be followed by a period of much lower mass loss, creating a relative void behind the first dense layer. Then, when the high mass loss resumes, it ejects a new dense shell that expands into that void. Over time, this creates the observed concentric structure. The submillimeter data, with its clues about clumpiness and complex chemistry within the shells, could be interpreted as evidence for this kind of ongoing, variable activity, where the wind never fully shuts off but instead pulses with a powerful, chaotic rhythm. The detailed submillimeter maps from ALMA are what truly bring this mystery to life. These aren't simple pictures, they are data-rich, three-dimensional reconstructions of the nebula's velocity, density, and temperature. They show the shells not as static sculptures, but as dynamic structures expanding outward at different speeds. They reveal subtle instabilities and ripples at the edges of the shells, hints of interactions with the interstellar medium or perhaps of magnetic fields shaping the flow. They even allow astronomers to peer slightly deeper, probing the warmer, denser regions closer to the star where new molecules might be forming before they are expelled into the colder outer shells. The powerful but puzzling submillimeter waves from the Fried Egg Nebula are therefore much more than a simple signal. They are a high-resolution diagnostic of a star caught in the act of monumental self-transformation, providing a detailed, if complex, chronicle of how the most massive stars slowly and dramatically unravel themselves, seeding the galaxy with the cold dust and complex chemistry that may one day form new planets and perhaps new life. Now we arrive at a celestial dance so perfectly strange it seems almost choreographed, a cosmic pas de deux performed by two stellar titans whose light tells a story of profound interconnection. Our 18th signal focuses on a system where two suspected hypergiants are locked in a gravitational embrace, but their light curves reveal a bizarre and counterintuitive relationship. When one star brightens, the other one systematically dims, and vice versa. This is the phenomenon of anti-correlated light curves, a delicate and precise cosmic seesaw that cannot be explained by the simple, well-understood mechanics of an eclipsing binary, where one star periodically passes in front of the other. In a standard eclipsing system, you'd see predictable, symmetrical dips in brightness as each star blocks the other's light. What we observe here is fundamentally different, a continuous, out-of-phase symphony of brightness changes that suggests a far more complex and intimate interaction between these two behemoths. The observational data that reveals this puzzle is both beautiful and confounding. Astronomers monitor the system's total light output over months and years, plotting it on a graph to create a light curve. For a typical variable star, this might show a single, repeating pattern. But for this system, when you apply sophisticated mathematical techniques to deblend the signal, you can disentangle two distinct light curves, one for each component. The result is astonishing. The two lines on the graph are almost perfect mirror images of each other. As the light from star A climbs toward a peak, the light from star B simultaneously falls into a trough. Then, as star A begins to fade, star B begins its own ascent. This precise anti-correlation is the hallmark of the system, a coordinated performance that points to a direct physical link between the two stars, a link that goes far beyond one merely casting a shadow on the other. Confirming the true nature of this system, however, is notoriously difficult, a challenge rooted in the sheer scale of the actors involved. These are hypergiants, stars so vast that their diameters can be measured in astronomical units, the distance between the Earth and the Sun. In a close binary system, their outer atmospheres could be so distended that they might actually be touching, swirling together in a shared, turbulent envelope. Furthermore, these systems are incredibly distant, and from our vantage point, the two stars appear as a single, unresolved point of light. We cannot simply take a picture to see them separately. Instead, we must infer their binary nature and their individual behaviors through the subtle, blended poetry of their combined light, a complex puzzle that requires powerful telescopes and sophisticated statistical models to even begin to decipher. So, what physical processes could be orchestrating this precise, anti-correlated dance? One compelling theory involves the profound effects of tidal forces. As the two massive stars swing around their common center of gravity, their immense gravitational fields exert powerful tidal pulls on each other, much like the moon raises tides on Earth's oceans but on a cataclysmic scale. This gravitational stretching could distort the stars from perfect spheres into egg-shaped ovals. As they orbit, the amount of surface area facing us would change. The theory suggests that these tidal distortions could be so extreme and so perfectly out of sync that when one star presents its broader side on profile to us appearing brighter, the other is presenting its more narrow end on profile appearing dimmer. Their continuous orbital motion would then create the observed see-saw effect in brightness, a kind of gravitational ballet where their changing shapes dictate their changing light. Another fascinating possibility is the phenomenon of mass transfer. In an incredibly close binary, one star can literally feed on the other. If one hypergiant has expanded to such a size that it overflows its gravitational Roche lobe, a stream of its outer atmosphere can be pulled away and onto its companion. This process could be the engine for the anti-correlation. Imagine that as star loses mass, its outer layers are stripped away, revealing hotter, brighter internal layers and causing it to brighten. Simultaneously, this stream of material slams into star B, creating a hot, bright accretion disk or impact zone that initially makes it brighter. However, if the transfer is unstable, the infalling material could also temporarily shroud star B in a dense, cool cloak of gas, causing its visible light to dim just as star A is brightening. The system would be in a constant state of flux, with the flow of mass directly dictating the balance of light between the two stars. A third and more subtle explanation involves the clever trick of reflected light. In this scenario, one of the hypergiants might be undergoing large, intrinsic brightness changes due to its own internal pulsations or eruptions. As it brightens, it floods its companion with intense additional light. The side of the companion star facing the brightening star would be strongly illuminated, much like the moon is illuminated by the sun. From our distant viewpoint, when the intrinsically variable star is brightest, we see it directly in its full glory. But we also see its companion primarily by the light it reflects, and if the companion's own intrinsic light is relatively constant, the reflected light from its partner could be a significant component of what we see. The anti-correlated light curve could then be an illusion of geometry. As the first star dims, the amount of light it shines on its partner decreases, making the partner appear to dim as well in a perfectly synchronized but inverse relationship. Each of these theories, tidal distortion, mass transfer, and reflected light, paints a picture of a deeply connected system, a binary pair whose fates are so intertwined that their most fundamental property, their brightness, becomes a shared and counterbalanced affair, revealing a level of stellar interaction that pushes the very boundaries of what we thought possible. From the intricate gravitational dance of binary hypergiants, we now turn to a solitary giant whose mystery is broadcast not in visible light, but in a faint, pervasive glow that permeates the cold spaces between the stars. Our 19th signal leads us to the remarkable red hypergiant VX Sagittarii, a pulsating behemoth located in the constellation of the Archer. This star is a known variable, rhythmically swelling and shrinking over a period of several years. But nestled within the broader emissions from its vast, dusty envelope, radio astronomers have detected something far more peculiar: a persistent, anomalous microwave emission. This is not the strong, coherent blast of a maser or the expected hum from hot gas. Instead, it is a faint, diffuse, and incredibly challenging to detect whisper of microwave light that stubbornly refuses to be explained by any of the standard processes we use to map the radio sky. To grasp why this signal is so baffling, we need to understand what it isn't. When astronomers look at the microwave universe, they are typically seeing one of two well-understood phenomena. The first is thermal emission from cold dust. Think of this as the gentle, warm glow of a heating element on a stove. As dust grains are warmed by starlight, they re-radiate that energy at longer microwave wavelengths. The second common source is synchrotron radiation, a non-thermal process where ultra-relativistic electrons spiraling at near-light speed around magnetic fields produce a powerful, broad spectrum of radio waves. The anomalous microwave emission from Vela Sagittarii fits neither of these profiles. Its spectrum, its unique signature across different microwave frequencies, has a distinctive peak and shape that doesn't match thermal dust models and is far too bright to be synchrotron radiation. It's an unaccounted-for ghost in the machine, a signal that appears as an unexplained haze in microwave sky maps, a subtle veil of radiation clinging to the star that cannot be attributed to the usual suspects. So, if it's not hot dust or speeding electrons, what could possibly be creating this persistent microwave whisper? The most promising and fascinating candidate involves a process that operates on an almost unimaginably tiny scale, spinning nanodust grains. Picture this: the circumstellar envelope around Vela Sagittarii is filled with dust grains of all sizes. Among them are the smallest of the small nanoparticles of carbon or other materials, each only a few dozen atoms across, smaller than a single strand of DNA. These tiny specks are so small that when they absorb a single photon of ultraviolet light from the hypergiant, the minuscule kick of energy is enough to set them spinning at phenomenal rates, billions or even trillions of rotations per second. This frantic rotational motion has a direct consequence. Just like a spinning electric charge creates a radio transmitter, these whirling nanograins themselves emit radiation, but at microwave frequencies. This proposed mechanism, known as spinning dust emission, could perfectly explain the anomalous spectrum that has puzzled astronomers for years. But this elegant solution introduces its own set of profound puzzles when applied to the extreme environment of a hypergiant. The first major hurdle is survival. The region close to a star like Vela Sagittarii is flooded with incredibly intense ultraviolet radiation. For delicate carbon-based nanograins, this is a hostile environment. The same UV photons that spin them up also have more than enough energy to blast them apart, breaking their atomic bonds in a process called photodestruction. For spinning dust to be the answer, there must be a continuous, prolific factory somewhere in the envelope that is constantly churning out these tiny particles faster than the star's radiation can destroy them. This suggests an ongoing, vigorous process of dust formation and fragmentation happening within the nebula, a veritable nano-assembly line working at a furious pace. Furthermore, the detected signal implies a population of these nanoparticles that is far larger than standard dust formation models predict. Where is all this nanodust coming from? One compelling theory is that it's the shattered remains of larger dust grains. In the turbulent, violent outflow from Vela Sagittarii, larger silicate or carbon grains could be constantly colliding with one another at high speeds. These collisions wouldn't just gently nudge the grains, they would shatter them, creating a cascading cascade of fragments down to the nanometer scale. It's a cosmic version of grinding sand into fine powder, with the hypergiant's own powerful winds providing the grinding mechanism. Another possibility is that the unique chemistry and condensation sequences in the star's cooling atmosphere directly favor the nucleation of these tiny particles over larger, more stable grains. The star might be an efficient producer of this exotic dust from the very moment the material is ejected from its surface. To visualize this, imagine a detailed microwave map of the region. Instead of a single, sharp point of light for the star, we would see a structured, extended glow surrounding Vela Sagittarii. Diagrams of the spinning dust mechanism often show these nanoparticles as tiny, gleaming spheroids, each with a dipole moment, a slight imbalance in their electric charge that makes them act like minute radio antennas when they spin. The anomalous microwave emission would appear as a diffuse halo around the star, its intensity tracing the dense, protected pockets within the envelope where these nanograins can form, spin, and crucially persist long enough to produce the collective signal we detect from Earth. The persistent anomalous microwave emission from Vela Sagittarii is therefore more than just a technical curiosity. It is a potential window into the poorly understood world of interstellar dust genesis and destruction, suggesting that the final stages of a hypergiant's life are not only about shedding solar masses of gas, but also about seeding its surroundings with a fine, spinning mist. Nanoparticles that speak to us in the faint, coded language of microwaves. Yet even as we listen to the faint microwave whispers of Vela Sagittarii, another hypergiant has been caught in the act of a far more dramatic and rapid transformation, a change written not in subtle heat but in the very elemental makeup of its visible atmosphere. This brings us to the 20th signal, a startling event centered on the yellow hypergiant Rho Cassiopeiae. For years, this star, one of the largest known in our galaxy, was a relatively stable, if variable, beacon. But recent spectroscopic observations have captured something truly extraordinary, a sudden and dramatic surge in the strength of helium lines in its spectrum. This isn't a gradual shift, it's a rapid, significant alteration of the star's atmospheric fingerprint, a clear sign that Rho Cassiopeiae's surface conditions have undergone a profound and unexplained upheaval. To appreciate the shock of this discovery, picture a stellar spectrum as a unique barcode of dark absorption lines, each one a chemical signature imprinted on the star's rainbow of light. For a star like Rho Cassiopeiae, the most prominent lines have always been those of hydrogen, the most abundant element in the universe. Helium lines were present, but they were faint secondary features in the overall composition. The event astronomers witnessed was like watching that familiar barcode suddenly reconfigure itself. Over a surprisingly short period, the helium lines intensified dramatically, growing much deeper and wider, while the hydrogen lines remained largely unchanged. This specific change is a direct and powerful diagnostic tool. In stellar atmospheres, the strength of helium lines is exquisitely sensitive to temperature and pressure. For these lines to strengthen so markedly, the layers of the atmosphere where they form must have become significantly hotter and possibly less dense. It's as if a veil has been pulled back, revealing a deeper, hotter layer of the star that was previously hidden from our view. So, what cosmic event could have caused such a rapid and specific revelation? One of the most compelling theories proposes that Rho Cassiopeiae violently ejected a shell of its own outer atmosphere. Imagine the star literally blowing off a significant portion of its hydrogen-rich outer layers in a sudden, episodic eruption. This ejected material would expand and drift away, effectively removing the overlying blanket of cooler gas. With this shroud gone, our spectroscopic view would now peer directly into deeper, hotter atmospheric layers where helium is more prevalent and the temperatures are high enough to excite helium atoms, causing them to absorb light much more strongly. This would be a stellar-scale version of stripping away topsoil to reveal the bedrock beneath, a dramatic act of self-excavation that fundamentally alters the face the star presents to the cosmos. A second, equally plausible hypothesis points to a massive internal convulsion known as a deep mixing event. Yellow hypergiants are notoriously unstable, with immense convection cells churning their interiors. It's possible that a powerful wave of turbulence, perhaps driven by a pulse in the nuclear burning shell deep within the star, surged all the way up to the surface. This colossal convective plume would have acted like a massive dredge, pulling up material from the hot, helium-rich interior and mixing it directly into the observable atmosphere. In this scenario, the star isn't uncovering a hidden layer. It's actively injecting it with fresh helium, enriching its surface in a single, violent overturning event that temporarily changes its entire chemical appearance. A third possibility involves a more subtle but no less extreme atmospheric instability. RW Cephei, balanced precariously on the edge of the Eddington limit, may have experienced a localized collapse or reorganization of its outer layers. A sudden drop in atmospheric pressure, even if temporary, could lower the density just enough to allow the already hot helium in the atmosphere to become a more dominant absorber of light. This wouldn't require a major mass ejection or deep mixing. It could be a purely hydrodynamic instability, a temporary shudder in the star's tenuous outer envelope that selectively amplifies the helium signal. The rapidity of the change suggests the trigger was swift, and the fact that the helium lines have remained strengthened indicates the star has settled into a new, albeit temporary, atmospheric equilibrium. The sudden strengthening of helium in RW Cephei is a direct observation of real-time stellar evolution, a live demonstration of how these colossal beings can reconfigure their very surfaces in human timescales, offering a rare and invaluable glimpse into the volatile mechanics that govern their final, unstable years. As we continue our exploration of these stellar enigmas, we arrive at a puzzle that strikes at the very language we use to understand the cosmos. Our 21st signal takes us to Lambda Cephei, a brilliant O-type hypergiant blazing with a fierce blue-white intensity. For decades, astronomers have studied its light, using spectroscopy to decode the chemical messages carried from its scorching atmosphere. In the visible spectrum, Lambda Cephei tells a relatively straightforward story, its absorption lines identifying the usual suspects of hydrogen, helium, and other common elements. But when we shift our gaze to the ultraviolet portion of the spectrum, the star's story becomes far more cryptic. Here, nestled among the familiar signatures, are a series of deep, dark absorption lines that stand as stark, unidentified features. These are not mere blips in the data. They are pronounced, consistent lines that stubbornly refuse to be matched with the known atomic or molecular transitions recorded in our most comprehensive laboratory databases on Earth. The process of identifying a spectral line is a meticulous and exhaustive form of cosmic detective work. Scientists take the observed wavelength of an absorption line and cross-reference it against vast digital libraries containing the unique fingerprints of every element and molecule we have ever studied. For the vast majority of lines, a match is found, revealing the presence and quantity of a specific substance in the star's atmosphere. But for these particular ultraviolet lines in Lambda Cephei, this process has hit a wall. Every possible candidate, from common elements in unusual ionization states to more exotic molecules, has been tested and rejected. The wavelengths simply do not align. It's as if we are listening to a symphony and hearing a series of clear, powerful notes played by an instrument we have never before encountered, a sound that exists outside all known musical theory. This failure to identify them points to a fundamental gap in our knowledge, suggesting that the physical conditions within this hypergiant's environment are so extreme that they are producing phenomena we have not yet learned to recognize. So, what could be the source of these mysterious ultraviolet signatures? One compelling line of investigation points toward highly ionized states of common elements. In the searing furnace of Lambda Cephei's atmosphere, temperatures and radiation fields are so intense that atoms can be stripped of many or even most of their electrons. We might be seeing the spectral signatures of bare or nearly bare atomic nuclei, for instance, an iron atom that has lost 20 of its 26 electrons. The problem is that the theoretical calculations for the exact energy levels and corresponding absorption lines of these extreme ionization states are incredibly complex and have not been fully mapped out for all elements. It is entirely possible that our current laboratory data is simply incomplete for these ultra-high-energy environments. The unidentified lines could be the long-predicted but never-before-seen fingerprints of matter pushed to its absolute limit, a glimpse into atomic behavior under conditions we cannot hope to recreate on our planet. An alternative and even more intriguing possibility involves the formation of exotic molecules. Conventional wisdom holds that the intense ultraviolet radiation flooding a hypergiant's atmosphere should tear any complex molecules apart almost instantly. However, some theoretical chemists propose that under these very conditions of extreme heat and pressure, transient, superheated molecules could form that are completely unknown in cooler environments. Picture a carbon monoxide molecule, but with its atoms held together in a different, more energetic configuration that is only stable at temperatures of tens of thousands of degrees. Or consider the possibility of metallic clusters, small, temporary groups of metal atoms like titanium or zirconium that form and dissipate in the stellar winds, absorbing light at very specific and currently unlisted ultraviolet wavelengths. These would be molecules born of fury, existing for mere microseconds in the star's violent outer layers, yet abundant enough to leave their collective mark on the spectrum we observe from light years away. To visualize this mystery, imagine a graph of lambda Cephei's ultraviolet spectrum. The horizontal axis represents wavelength and the vertical axis shows the intensity of the light. The graph is not a smooth curve, it is a forest of sharp, narrow dips, the absorption lines. Most of these dips are labeled with familiar names: carbon Roman 4, silicon Roman 4, nitrogen V. But then, scattered through this forest are several deep, unmarked valleys. These are the unidentified features, standing in stark contrast to their identified neighbors. In a detailed, multi-panel illustration, one could see a close-up of one of these mysterious lines with a question mark hovering over it. Next to it, a diagram might show an artist's conception of a hypothesized exotic molecule, a tiny, intricate structure of atoms glowing with intense energy as it forms in the star's turbulent atmosphere, only to be ripped apart a moment later by the very forces that created it. The presence of these unidentified lines in lambda Cephei's ultraviolet spectrum is a humbling and thrilling reminder that even our most advanced tools and theories have their limits, and that the universe still holds fundamental secrets about the very nature of matter and energy in the most extreme laboratories it possesses. Just when you think you've seen every form of hypergiant variability, the universe unveils a rhythm so precise and interconnected it feels almost orchestrated. Our 22nd signal brings us to the magnificent red hypergiant KY Cygni, a star whose slow, majestic heartbeat reveals a profound mystery when we listen to its voice across two very different parts of the spectrum. Imagine a star that breathes, expanding and contracting over a period that stretches hundreds of days. Now imagine that this same deep, rhythmic pulse not only changes the star's visible brightness, but also simultaneously modulates the strength of its radio emission, as if the star's entire extended atmosphere, from its scorching surface to its cold outer layers, is moving in perfect, unified harmony. This is the coordinated dance of KY Cygni, a phenomenon that links processes separated by billions of kilometers and challenges our understanding of how a star's internal vibrations communicate with its outermost reaches. The observational evidence for this coordination is both elegant and startling. Astronomers meticulously monitor KY Cygni over many years, creating two separate light curves, one for its optical brightness, the light our eyes can see, and another for its radio flux, the faint whisper of its cooler, extended atmosphere. When you place these two graphs side by side, the correlation is undeniable. Both curves rise and fall with the same long, deliberate period, typically on the order of several hundred days. As the star grows brighter in visible light, reaching the peak of its pulsation, the radio emission also swells to its maximum intensity. Then, as the star dims optically, the radio signal fades in perfect synchrony. This lockstep relationship is the crucial clue. It tells us that the mechanism driving the optical changes is not confined to the star's photosphere. its influence extends powerfully and directly into the vast circumstellar envelope where the radio waves are born, a region that can be thousands of times larger than the star itself. This synchrony presents a direct challenge to standard stellar pulsation models. In a classic picture, a star like KY Cygni pulsates due to instabilities in its interior, causing its surface to periodically heat, expand, cool, and contract. This explains the optical variations beautifully. However, these models often treat the radio-emitting region, the extended envelope of gas and dust, as a separate entity, influenced by the star but not necessarily dancing to its immediate rhythm. The radio emission is typically generated by the thermal radiation of ionized gas or by maser action in molecules like silicon oxide, processes thought to depend on local conditions in the wind, such as density and temperature, which were not expected to vary so precisely in time with the star's heartbeat. The fact that the radio flux mirrors the optical pulsation so perfectly means there must be a far more efficient and rapid coupling between the star's pulsating surface and its distant atmosphere than our traditional physics accounted for. It's as if a drummer's beat is not only heard by the musicians standing next to them, but is also felt instantly and simultaneously by every single instrument in a massive, stadium-filling orchestra. So, what physical bridge could possibly connect the star's photosphere to its radio-emitting envelope with such remarkable fidelity? One compelling theory involves the concept of global pulsations with far-reaching consequences. When KY Cygni expands during the bright phase of its pulsation, its surface not only grows larger but also cools slightly, and its gravity weakens at the outer boundary. This physical expansion could trigger a chain reaction. The weakened gravity might allow the star's own intense radiation pressure to push more effectively on the inner layers of its stellar wind, driving a denser, more massive outflow of material. This enhanced wind would then propagate outward, and when it reaches the specific distance where radio-emitting molecules like silicon oxide are concentrated, it would compress and heat the gas, increasing the efficiency of the maser action and causing the radio flux to brighten in sync with the optical peak. The entire circumstellar envelope would be responding to the star's pulsation as if it were a single, cohesive entity, with changes at the surface sending a wave of influence that restructures the outer atmosphere almost instantaneously on an astronomical timescale. Another fascinating hypothesis focuses on the role of luminosity and its direct impact on the wind. The pulsation of a red hypergiant isn't just about size, it's also about the total amount of light it emits. As the star pulsates and its optical brightness increases, its overall luminosity, the total energy output across all wavelengths, also rises. This surge in radiant energy floods the circumstellar envelope with more intense ultraviolet and visible photons. These photons can ionize atoms and excite molecules, directly pumping the energy levels required for the radio masers to operate. In this scenario, the radio brightening isn't due to a density change from a wind, but rather a direct response to the increased pumping radiation from the pulsating star. The masers in the envelope act like a natural amplifier whose power supply is directly wired to the star's own variable brilliance. The coordinated oscillation is then a simple, direct cause and effect. The star brightens, pumping more energy into the maser zone, and the radio signal amplifies in perfect time. Perhaps the most complex theory involves the propagation of actual shock waves. The pulsation of a hypergiant is not a gentle, smooth motion. It can be a violent oscillation that generates powerful shock fronts at the star's surface. These shocks would then travel outward through the stellar wind at supersonic speeds. When one of these shock fronts slams into the dense molecular layers of the envelope where radio masers form, it would violently compress and heat the gas, creating a temporary, brilliant spike in radio emission. The slow, hundreds of days period of the pulsation would then set the clock for the timing of these shock arrivals, creating the observed synchrony between the optical pulsation cycle and the radio flux variation. In this model, the coordination is not instantaneous, but it is predictable and locked in phase, with the shock wave acting as a messenger that faithfully carries the news of the star's internal rhythm to its distant atmospheric frontiers. The coordinated oscillations of Ky Cygni thus reveal a star that functions as a deeply interconnected system, where a shudder in its core can orchestrate a symphony of light and radio waves across the breathtaking expanse of its own stellar empire. Now let's journey from the harmonious oscillations of a single star to a gathering of titans, a place where we expected a cosmic fireworks show of the highest energy, but instead found a profound and puzzling silence. Picture a stellar metropolis, a dense cluster of hypergiant stars, each one a raging furnace of radiation and ferocious winds. With so many colossal engines packed into a relatively small volume of space, you would naturally expect the environment to be a maelstrom of high-energy violence, a natural laboratory for particle acceleration on a grand scale. Yet, when astronomers point their most sensitive gamma-ray telescopes toward this cluster, they are met with a baffling quiet. This region stands as a conspicuous gamma-ray quiet zone, a pocket of unexpected calm in the gamma-ray sky that defies our basic predictions about how the most massive stars should interact with their environment. To understand just how counterintuitive this silence is, you need to consider the phenomenal forces at play within a hypergiant cluster. Each of these stars is blowing a hurricane of charged particles, a stellar wind, that carries away a mass equivalent to our entire Earth every year and does so at speeds of millions of kilometers per hour. Now cram a dozen or more of these stars into a region that, in cosmic terms, is like a crowded downtown square. The winds from these stars don't just flow out peacefully, they violently collide with one another. Where these supersonic flows smash together, they create immensely powerful shock fronts, regions of chaotic and seething plasma. These shocks are, in theory, perfect natural particle accelerators. They should take electrons and atomic nuclei and whip them up to velocities infinitesimally close to the speed of light, turning them into what we call cosmic rays. And when these ultra-relativistic particles then collide with photons of starlight or with other particles in the dense cluster environment, they should produce a brilliant and diffuse glow of gamma-ray photons, the most energetic form of light in the universe. The expectation was that this cluster would be a bright, extended beacon in gamma-ray sky surveys, a shining example of collective stellar fury. The observational evidence, however, tells a very different story. Wide-field images from space observatories like the Fermi Gamma-Ray Space Telescope map the entire sky in gamma-ray light. In these maps, you typically see bright, diffuse structures corresponding to supernova remnants, pulsar wind nebulae, and the tangled gas clouds of the galactic plane. Then you find the location of this hypergiant cluster, often marked with a circle or an annotation. And right there, where our models predicted a brilliant hotspot, the map shows a distinct and troubling lack of signal. It's not just faint, it's conspicuously empty compared to its bustling surroundings. It's as if you were listening for the roar of a massive waterfall in a silent forest. The absence of the expected sound is in itself a powerful and perplexing piece of data. This quiet zone forces us to ask not what is producing gamma rays, but what is actively preventing their production or hiding them from our view. So, what cosmic mechanism could be suppressing this high-energy light show? Astronomers are investigating several compelling possibilities, each pointing to a different form of astrophysical regulation. One leading idea is that of extremely efficient particle cooling. It's possible that the particle acceleration is indeed happening, but the environment within the cluster is so dense with radiation and magnetic fields that the cosmic rays lose their energy almost as soon as they gain it. Imagine trying to heat a pot of water on a blast furnace, but the pot has a massive hole in the bottom. The energy input is tremendous, but it's instantly carried away. In this case, the accelerated particles might be radiating away their energy through other channels, for instance, by producing intense X-rays or synchrotron radiation before they ever have a chance to interact and create gamma rays. The engine is running, but its high-energy exhaust is being converted into a different, less detectable form of waste heat. Another fascinating hypothesis focuses on the configuration of magnetic fields within the cluster. Magnetic fields are not just passive features, they can act as cages or guides for charged particles. It's possible that the tangled web of magnetic fields generated by the collective action of all these hypergiants is structured in a way that actually suppresses efficient particle acceleration. Instead of the shock fronts acting as focused accelerators, the magnetic fields might be so chaotic that they prevent particles from being trapped and gaining energy in the shock regions. Alternatively, the fields could be so strong that they simply deflect incoming cosmic rays, preventing them from building up to the high densities required for a detectable gamma ray signal. The cluster could be surrounded by an invisible magnetic shield, a force field that contains its own high-energy particles or deflects external ones, creating a bubble of gamma-ray quiet in an otherwise active galaxy. A third and more straightforward possibility is that we have simply overestimated the ability of these colliding winds to produce gamma rays. Perhaps the wind speeds, while immense, are just below the critical threshold needed to generate the most powerful shocks. Maybe the distances between the stars, though small to us, are just large enough that the wind collisions occur at lower densities than our models assumed, resulting in weaker shocks and less efficient acceleration. Or the stellar winds themselves might be leaky, with much of their energy being dissipated in other ways, such as through powerful sound waves or turbulent heating, rather than being channeled into particle acceleration. The quiet zone might not be an active suppression, but simply a testament to the fact that the precise Goldilocks-like conditions required for copious gamma-ray production are more special and harder to achieve than we initially thought. This great silence from a gathering of stellar titans is a powerful reminder that the universe often reserves its most profound lessons not for what it reveals, but for what it unexpectedly withholds. But just as we grow accustomed to the profound silence of one cluster, the universe delivers a whisper from a star that should have been completely mute. Our 24th signal presents us with one of the most chemically paradoxical discoveries in modern astronomy, the transient detection of a water maser emanating from a blue hypergiant. This is the stellar equivalent of finding an ice cube blazing in the heart of a blast furnace. Blue hypergiants are among the hottest, most luminous stars known, with surface temperatures soaring to over 30,000 degrees Celsius. Their intense ultraviolet radiation floods their immediate surroundings, creating an environment so hostile that any water molecule venturing too close is instantly ripped apart into its constituent hydrogen and oxygen atoms. The very existence of a water maser here, a phenomenon that requires stable, cool, and dense gas to operate, is a direct contradiction to our fundamental understanding of stellar environments and the chemistry they permit. To grasp just how anomalous this is, we need to revisit what a water maser needs to thrive. A maser, the microwave cousin of a laser, acts as a natural amplifier. For a water maser to flare into existence, you need a precise combination of conditions. First, you need a plentiful supply of water vapor. Second, this vapor must exist in a region that is relatively cool, typically only a few hundred to 1,000 degrees Kelvin, a far cry from the tens of thousands of degrees at a blue hypergiant surface. And third, the gas must be dense enough for the water molecules to be frequently excited or pumped by a source of energy, often infrared radiation from warm dust. These conditions are routinely met in the extended, cool envelopes of red supergiants and in the placid cocoons of newly forming stars. Finding a water maser around a searing blue hypergiant is like hearing a perfectly tuned choir singing from inside a volcano. The environment is simply too violent and destructive for such a delicate phenomenon to survive. The discovery itself was as fleeting as it was shocking. Radio astronomers, meticulously mapping the sky, noticed a single, brilliant spike at the characteristic 22 GHz frequency of water maser emission. This spike was unmistakable, a narrow, intense beacon standing out starkly against the background radio noise. But when they pointed their telescopes back to the same coordinates weeks or months later, hoping to confirm the find, the signal was gone. It had vanished without a trace. This transient nature is a critical piece of the puzzle. It tells us that whatever created the conditions for the water maser was not a permanent feature of the star. It was a temporary, likely violent, event that briefly reshaped the star's immediate environment before the relentless UV radiation from the hypergiant reasserted its dominance and dissociated the water molecules back into atomic gas. So, what cataclysm could have momentarily forged a cool, dense oasis around this stellar inferno? One of the most compelling theories points to a recent colossal mass ejection. Imagine the blue hypergiant undergoing a violent paroxysm, violently expelling a massive shell of its own outer atmosphere into space. As this enormous blob of gas travels away from the star, it expands and cools rapidly. For a brief window of time, this ejected material could form a temporary protective shroud. The inner layers of this shell, still dense and now significantly cooler than the star's surface, could provide the perfect nursery for water molecules to form and persist. The intense radiation from the hypergiant would still be pumping the molecules, but the dense, cool gas of the shell would allow the maser action to amplify, creating the brilliant but short-lived radio spike we observed. Once the shell expanded too much, thinning out and allowing the destructive UV photons to penetrate, the delicate maser conditions would be erased and the signal would vanish as quickly as it appeared. An equally fascinating possibility is that we are not listening to the blue hypergiant alone, but to a hidden dance partner. This theory proposes the existence of a previously unseen cool companion star, perhaps a massive red supergiant or an oxygen-rich asymptotic giant branch star orbiting the blue hypergiant. In this scenario, the water maser would originate not from the blue hypergiant's environment, but from the vast, cool circumstellar envelope of its fainter, cooler companion. The transient nature of the signal could then be explained by the turbulent and clumpy nature of that companion's wind. A particularly dense clump of gas, rich in water vapor, might have drifted into our line of sight, acting as a natural amplifying lens that focused the maser emission into a brilliant, temporary beacon. The challenge with this theory lies in the sheer power of the blue hypergiant. Its ferocious radiation and powerful wind would likely evaporate or violently disrupt the outer envelope of a close-in companion, making the survival of a stable water maser zone in such a binary system a delicate balancing act. This single, evanescent whisper of microwave light forces us to confront the dynamic and episodic nature of stellar evolution. The transient water maser from a blue hypergiant is more than just a curiosity. It is a potential snapshot of a star in a moment of extreme crisis, caught in the act of violently reshaping its own identity. It suggests that even the hottest and most seemingly stable stellar behemoths can undergo convulsive transformations, momentarily creating conditions around them that defy their very nature. This fleeting signal is a powerful reminder that the cosmos is not a static collection of objects, but a living, breathing, and often violently changing system, where the most profound mysteries can appear in an instant, only to fade away before we can fully grasp their meaning. And so we reach the grand finale of our cosmic tour, a signal that pushes the boundaries of detection itself and offers a glimpse into a future where we don't just see or hear the universe, but we can actually feel its deepest vibrations. This brings us to our 25th and final unexplained signal, the tantalizing, yet still unconfirmed, candidate for a low-frequency gravitational wave emitted by a hypergiant star system. To understand why this potential discovery is so revolutionary, we first need to grasp what gravitational waves actually are. picture the fabric of space-time not as a static stage, but as a vast, flexible trampoline. When massive objects move or accelerate, they create ripples in this fabric, much like a spinning dancer would cause the trampoline surface to wobble. These ripples are gravitational waves, incredibly faint distortions that travel outward at the speed of light, stretching and squeezing everything in their path by an almost imperceptible amount. For decades, they were purely theoretical, the final, unproven prediction of Einstein's general theory of relativity. The first direct detections, which rightly won a Nobel Prize, came from the collisions of black holes and neutron stars. These are catastrophic, violent events where immense masses accelerate to a significant fraction of light speed in a fraction of a second, creating a loud, high-frequency chirp in the gravitational wave spectrum. Detecting the much quieter hum from a hypergiant star is an entirely different and far more difficult challenge. The instability or merger of a hypergiant system would not produce a brief, sharp chirp. Instead, it would generate a long, low-frequency rumble, a monochromatic drone that could last for months or even years. The problem is that our current ground-based detectors, like LIGO and Virgo, are deaf to these low frequencies. Their measurements are drowned out by terrestrial noise, everything from seismic activity to the rumble of distant ocean waves. To hear this particular cosmic melody, we need to listen from the quiet of space. This is where the data anomaly comes in. While no official confirmation has been announced, astronomers working with pulsar timing arrays have reported a curious, persistent signal in their data. Pulsar timing arrays are, in essence, galactic-scale gravitational wave observatories. They use a network of incredibly stable millisecond pulsars, the dead, spinning remnants of stars, as a celestial metronome. By meticulously monitoring the arrival times of their pulses across the galaxy for years, scientists can detect minute variations. If a gravitational wave passes between us and one of these pulsars, it will slightly alter the distance the radio waves have to travel, causing the pulse to arrive a fraction of a second early or late. The intriguing signal in question is a low-frequency background hum, a common noise signal that seems to be affecting many of the pulsars in the array in a correlated way. While the leading candidate for this background is the combined rumble from countless merging supermassive black holes across the universe, a small but compelling faction of researchers has not ruled out a different contributor, a nearby monstrous source like a merging hypergiant binary system in our own galactic neighborhood. Imagine the scenario that could produce such a signal: two hypergiant stars, each hundreds of times the mass of our Sun, locked in a final, slow death spiral. As they orbit each other, their immense gravity relentlessly pulls them closer, and this accelerating dance radiates energy away in the form of gravitational waves. Unlike the frantic final moments of a black hole merger, this process could take centuries, emitting a steady, low-frequency note. Alternatively, the signal might not come from a merger at all, but from a single, profoundly unstable hypergiant. If such a star were to undergo a massive, asymmetric convulsion, a colossal starquake on its surface, or a sudden, lopsided ejection of material, the resulting jolt could also send gravitational ripples across the cosmos. The specific character of the anomaly in the pulsar timing data, its frequency and amplitude, is what has prompted this speculative but thrilling line of inquiry. The implications of verifying this signal are nothing short of profound. It would open a completely new window into the inner workings of these colossal stars. Throughout this journey, every signal we've explored has been carried to us by electromagnetic radiation, light, radio waves, X-rays. These signals can be blocked, scattered, or absorbed by dust and gas. They only tell us about the surface of a star or its immediate surroundings. Gravitational waves, however, pass through matter unimpeded. They are a direct telegram from the gravity of the object itself. Detecting them from a hypergiant would allow us to peer, for the first time, directly into its heart. we could probe the dynamics of its core, the physics of its nuclear furnace, and the precise mechanics of its instability in a way that is simply impossible with light alone. We would no longer be just astronomers, we would become true cosmic listeners, feeling the very vibrations of space-time to understand the most powerful engines in the universe. Visualize this for a moment, an animation showing a hypergiant binary system, two titanic orbs of fire slowly spiraling inward, with ripples spreading out from them like waves from stones dropped in a pond. These ripples propagate across the galaxy, eventually washing over our solar system. The animation then cuts to a schematic of a pulsar timing array, with lines connecting Earth to various pulsars across the Milky Way. As the gravitational wave passes through, these lines subtly stretch and compress, and the predictable rhythm of the pulsar's flashes is shown to jitter ever so slightly on a graph. This is the delicate, precise experiment that is currently underway, an effort to sift a single, monstrous whisper from the background noise of the entire cosmos. The ongoing efforts to verify this signal involve collecting more years of data, adding more pulsars to the array, and developing ever more sophisticated algorithms to filter out noise. It is a painstaking global collaboration, a testament to human curiosity and our relentless drive to understand the universe not just by looking, but by listening to its deepest, most fundamental rhythms. This candidate signal, whether confirmed or not, represents the thrilling frontier of astrophysics, a future where we will feel the universe tremble and in those tremors read the hidden stories of its greatest giants. We have traveled across the cosmos together, from the erratic heartbeat of a dead star to the ghostly whisper of a gravitational wave, witnessing 25 profound mysteries that challenge our very understanding of the universe. These are not mere anomalies, they are the fundamental language of hypergiants, a collection of voices speaking in dialects of energy, chemistry, and gravity that we are only just beginning to translate. Each one represents a frontier, a place where our current models of physics reach their limits and the great, dark unknown begins. They remind us that the universe is not a static museum exhibit, but a vibrant, dynamic, and often violent living entity, constantly evolving and surprising us at every turn. What ties all these signals together is their incredible power to force us to rethink. The steady radio hum of HD 179821 is as revolutionary as the explosive tantrums of Rho Cassiopeiae because they both defy expectation. One shows us that silence can be as profound as a scream, while the other demonstrates that stellar death can be a series of violent preludes rather than a single, final act. The coordinated flares of S. Doradus teach us that a star can act as a single, interconnected system, while the chemical paradox of Mu Cephei reveals that the very elements of our world can be dredged up from stellar furnaces in ways we never anticipated. These are not isolated curiosities, they are interconnected pieces of a grander puzzle, each one informing our understanding of the others and painting a collective picture of stellar evolution that is far more complex and wondrous than we ever imagined. Now the conversation turns to you. After this incredible journey, we want to know which of these cosmic enigmas captured your imagination the most. Was it the legendary wow signal and the tantalizing possibility that a hypergiant could mimic an artificial broadcast? Or perhaps the high-velocity bullets fired by Zeta puppies, revealing a star as a cosmic cannon? Maybe the profound silence of the gamma-ray quiet zone, where a gathering of titans defies our predictions, struck you as the most humbling. Head to the comments and share your thoughts on which signal you find the most baffling and why. Your perspective adds another valuable dimension to this ongoing cosmic dialogue. The investigation into these stellar giants is far from over. It is a story still being written, with new chapters being added every time a telescope is pointed at the sky or a new dataset is analyzed. The universe is actively communicating with us, and these 25 signals are just the beginning of the conversation. If you found this journey to the edge of our understanding as thrilling as we did, be sure to like this video, subscribe to the channel, and tap the notification bell. There are countless more cosmic mysteries waiting to be unraveled, from the enigmas of dark matter to the secrets of the early universe, and we will be exploring them all together in the videos to come. Thank you for joining us on this